Morning, Johnny. We'll get started in a second. Did you guys, sorry, Johnny, did you have any questions on the problems that we did for homework? Actually, I can work with you for a few minutes here while we wait. I know other people might have questions too. Interesting. Okay. Problem 3. Okay. Great. Yeah, I didn't think it would be easy for. I think I didn't really talk too much about how to solve that. So maybe we can just get started with that and just take a look and see. Let me just jump into those problems though. Here we go. Problem number 3. Oh, yeah, that's a good one. Okay. So cool. Why don't we take a look? Did you figure it out or? Good morning. Good morning. Did you figure it out or did you get stuck? I didn't get stuck. Okay. So let's yeah, I mean we're gonna end up talking about this, but here's the basic idea, right? The idea is you have two particles and they happen to have the same mass and they happen to be both electrons, so they have the same charge, right? So if they're initially together and at rest, you can say to yourself, what kind of energy would that be? And the answer is, well, that's electric potential energy, right? The starting energy is electric potential energy. And if you remember the formula, it's K Q1 Q2 divided by R. Right, that's the equation. Okay, so then the idea is they're going to fly apart. Okay, so and by the way, when they're very far away from each other, they're going to each have a velocity. But here's the question: when they're very far apart, do they have the same speed or a different speed? And that's actually something kind of important that you need to remember. Do they have the same or different? And the answer to that question is they must be the same, right? Of course they are. Why? Well, it turns out it's from conservation of momentum. So if you're not moving, right, if your speed is 0, then what's your momentum? Well, the momentum's 0. So the initial momentum of the electrons being at rest is 0. So what's the final momentum? It's also 0, right? This is a weird idea, but super, super cool and super interesting. That how is it possible that two things that are moving have 0 momentum? And the answer is because momentum has direction. It's a vector, okay? So if we call forward, we call to the right positive, to the left negative. This particle has to have the same amount of negative momentum as this particle. So what you know is that the speed, so we have, the mass times the final velocity, this particle 1's final velocity, plus the mass of the electron times particle 2's velocity, final velocity, have to add up to 0, right? They have to be 0, which means that these two velocities are just opposites of each other. Okay, So the electrons are traveling with the same speed and opposite direction. Okay, so now what? Well, so now that we know that the same speed, we can go ahead and finish the problem, right? And we're going to use conservation of energy. So the initial potential energy that we have is going to turn into the kinetic energy. The kinetic energy for the first particle plus the kinetic energy of the second particle. Because they're going the same speed, they're going to have the same kinetic energy. So you could say 2 times the kinetic energy of either one. So what that tells me is the kinetic energy of one of the particles is exactly 1/2 of the original potential energy. And now I can put in the numbers and you can solve for the speed that way. Okay, so that was a little tricky. We'll see if somebody got the problem answered for us. But that's how you were supposed to approach it. Okay, so if you didn't get 3, you probably had a hard time with that bonus question too, or maybe 4 as well, right? The protons. Okay, all right, great. Good morning, everybody. How are you? Let's see, I'm gonna turn on my face here. Who do we got? We got,
Can you hear me, Sean?
Bonnie, Julian, Sam, Steve, Johnny, Kenny. Okay, great. Nice to see you guys. Julian, did I say everybody? Okay. Good morning, good morning. So let's see.
Hello.
We have a lot of stuff that we can talk about today. Here's Tom. Okay, Tom is coming onto Zoom. Okay, so the Zoom is better for interaction. And nobody is on YouTube. That's fine. We'll just record it for anybody who has to come later. Okay. Sorry, question, comment? Good morning. You can talk if you want. Is that Tom? No, that's Kenny.
Yeah, can you hear me?
Hey, Kenny. So that was just before class. So yeah, that homework was difficult. Oh, good. Oh, I'm so glad. That's wonderful. I hope it was no, I'm sorry. If it was too difficult, then maybe what it means is I didn't really prepare you very well. So why don't we get started? Before we get started, though, I just want to remind you guys, we do have a guest speaker right after class today. And if you're looking for an outside activity, many of you maybe do already, but if you're looking for an outside activity or just want to hear an interesting talk, we have Jared Goldberg speaking to us for the Astronomy Club. And I'll be setting that up right after class, and it'll be on YouTube, right? So then actually you can ask questions. I think I put a little bit of something there. I don't know if anybody is interested. You may or may not be, but I will actually give you extra credit if you ask Jared a question, a good question. If it's just a question like, what's your favorite color? That doesn't count. If you're asking him, you know, his favorite brand of I don't know, whatever. But ask him a question about stars and about how they live and die. I think you'll find it very interesting. He has spoken at the Astronomy on Tap a couple of times, and so he's probably going to be repeating a lot of that material, but there's always a way to hear something fresh. So even if you've gotten to go to the Astronomy on Tap, I think it would be worth listening to him. So that'll be today at 1 p.m. Okay, so we had some difficulties. So why don't we go ahead and start at the beginning? Who had difficulty with the first problem? Anybody have problems with the first problem?
That was fine.
That was okay. Okay, so can we get some answers just to make sure that we have some consistency?
So
the first question was asking, it was question 0, sorry, right? If you know that the charge of an electron is this elementary charge, 1.602 times 10 to the minus 19 coulombs, then how many do you need, right? That's one, I should have put 1 elementary charge. If your charge is 1 coulomb, how many electrons would that be, or are either gained or lost electrons? Okay, and the number was, who got a number?
6.242 times 10 to the 18.
242 times 10 to the 18th. Did anybody else get that answer? Anybody else get that answer? Can we get a confirmation, please?
I guess I just don't understand how you figure it out. I don't know how you got to that number to begin with, really.
Oh, okay. All right. So here's the idea. Do you understand this idea? that the charges, whatever they are made up of either gained electrons or lost electrons. Anytime you have a charge, it's made up of some number. This is a number. We're looking for this number, right? So if I say 1 coulomb equals N, which is what I'm looking for, I meant to put the parentheses over here, 1.602 times 10 to the minus 19, then how do you find N? You just divide both sides by 1.602. So now, if you didn't know how to do it, I know you can do this. This is not that hard, right? We're just trying to figure out how many of them do you need in order to get up to this charge. And you want to find out that it's huge. It's a huge number of charged particles. And that's why this charge that we talk about, this is actually a really big charge, by the way. I'm not saying you can't come into contact with this, but this is a very large amount of charge. And it corresponds to a huge number of electrons, almost a mole of electrons, not quite, right? Okay, sorry, I meant to just cross that off. So anybody confirm? Can we get a confirmation, or should I just do it? Okay, I thought the number was pretty close to 6 times 10 to the 18th, but I'll just go ahead and do it. Anybody confirm? I got the same answer.
Yeah, Johnny confirms.
Oh, he did? Oh, okay, great.
Yeah, I also just got it right now.
Okay, all right. So then, so that was part A, right? Part B was, what about something that's more reasonable? By the way, if you rub a balloon on your head, then the charge that you get is something like on the order of microcoulombs, might even be tens of microcoulombs, okay? And this is, so in other words, this is a typical charge that a human might come into contact with. And so what is this? This is 1 times 10 to the minus 6 coulombs. So again, how many electrons or how many either gained or lost electrons would it take to make this?
So you basically just minus 6 to.
Yeah, I mean,
18.
basically, yeah, the only thing is going to be, what would it be?
Minus 6, so 12.
6.242 times 10 to the 12. Okay,
Yeah.
It's still a huge number. And then the last part, right? Even it's just huge, right? What is this? 10? What's 10 to the 12? That's trillion. 6 trillion electrons, right? 6 trillion either gained or lost electrons. And finally, this is the charge on maybe a piece of dust, right? Or a small something. It's a nanocoulomb. And so it's 1 times 10 to the minus 9. And all it is what? 6.242, 10 to the 9. It's still billions, right? Okay, so that was problem 0. Everybody got problem 0. Okay, how about problem number 1? Anybody get any answer?
This one, I was kind of worried. I don't know. I feel like answers 2 and 3 were, well, 1 is I got for the electron positive, or yeah, positive.
Right, so the electron, because it's negative, right? It's a negative, falls toward the positive, right? The positive terminal of the voltage, the positive terminal of the positive plate, right? So falling indicates what? When I say fall, what do I mean by that? Losing potential energy.
Losing potential energy.
Yeah, losing potential energy. You lose potential energy, you're falling. It's done spontaneously, right? Nobody needs to help you fall, you just fall. And so electrons fall towards the positive, protons fall towards the negative, right? And that's just kind of a cool thing. We're not talking about gravity fall, right? We're talking about losing PE, right? In this case, it's electrical potential energy, not gravitational potential energy. Okay, so part A. And the part B, what was the second question? It was, what is the kinetic energy in electron volts after being accelerated? So if this was hard, what I want you to do is, I wanted you to actually understand something. And by the way, this is a real number. This is taken from my Hitachi scanning electron microscope days. The change in the voltage, the change in the potential was 300,000 volts. Okay, this is often the way we write it. Okay.
Yeah.
And therefore, if you take an electron and you move it through a delta V of 300 kV, then in fact, this is exactly the change in the
Same.
kinetic energy, because this is the
Yeah.
change in the potential energy. So the answer was 300
Okay.
keV. Okay.
Okay, cool.
In other words,
Well,
it's
I
like
put
totally simple, right? There's no thinking involved. You just
I only
know.
got that after doing the math.
I got
know.
you, but that's actually really fun. I'm glad that you did. But then I want you to understand that what a particle physicist does is thinks this way first, right? So this is actually a simple idea that the electron or the proton must gain the same amount of energy, right? If they fall through the same potential difference because they have the same magnitude charge, then they have the same amount of kinetic energy when they're done. Are they moving the same speed?
the proton and the electron.
The proton and electron, yeah.
Yes, they're moving this. Oh no, they're not moving the same speed, but they have the
Of
same
course
energy.
they're not moving the same speed. Why not?
Because the proton is much heavier.
Totally, right? Thousands of times heavier, like almost 2,000 times more massive. And therefore, is it moving faster or slower?
Slower, and we had to derive gamma, right?
Did you need to derive gamma? I don't know.
'Cause That's
Did
what
you?
that's what I did. I derived gamma so that we could.
Okay, so you know that this is the kinetic energy. You know that. How do you convert it into joules? It was actually, again, you could just do this. It's going to be 1 joule is 1.602 times
You
10 to
could
the
take
minus.
the amount of electrons that you need, because 1 electron volt is 6.24 times 10 to the 18 per joule, right? You need 6 times 10, 6.242 times 10 to the 18 electron
Sure.
volts per joule. So if
Sure.
you found the joules, you could just use that as a conversion, right?
Absolutely. Yeah, that's just this inverted, right? Absolutely. That's fine. So that's perfect. And you got the same answer that we're about to get right here. So you take 300 times 10 to the third. This is a weird way to put it, but I'll leave it. And you're multiplying by the conversion factor. So instead of, that's basically what you did, is you divided by that 6.4. And right, Christian? Okay, and that's fine. Actually, what you did is it's exactly the same calculation. So dividing by that 6.4242 number is the same thing as multiplying by the 1.602 number. Okay, so you don't get a very big number. Somebody give me an answer. What's our
It's
answer?
a 4.806 to the negative 14.
10 to the minus 14. Okay, that seems pretty small, doesn't it? Doesn't that seem pretty small?
It is a single electron, right?
It's a single electron with an incredibly small mass. What's the mass of an electron? 9.11, 10 to the minus 31. Okay, then you say, wow, it actually is pretty big. Okay, this is the rest mass. And because we did the problem last Friday, you knew, is this a relativistic problem or not?
It is.
It is totally a relativistic problem. So there is no other way to solve it. You must use the relativistic formula for kinetic energy. Once you know that something is relativistic, you basically, I mean, you could try to solve it the other way. Once you get a speed that's a significant fraction of the speed of light, you screwed up. You're supposed to use the relativistic formula. What's the relativistic kinetic energy? Gamma minus 1 mc squared. Okay.
And so we know gamma.
Okay, so let me just show you a slick trick in case you guys didn't see this. This thing right here is actually, for a particle physicist, something that they know very well. It's 0.511 MeVs. So I just want to share with you that you could do it a little bit harder, which is not wrong, it's fine. Or you can actually use this equation right here. So if I go back to the original kinetic energy, which, by the way, what's another way to put this? This is 0.3 MeV. .300, I guess. Okay. So in other words, 0.3 MeV equals gamma minus 1, 0.511 MeV. Wow, right? That's simple.
Yes.
Okay. So divide by 0.511. But it's okay if you didn't do it this way. I only want to show you that this is one possible way. This is what a particle physicist would do though, right? Because it
Yeah.
makes it's super simple and fast, right? So gamma is just 1 plus 0.3 over 0.5, which is what, whatever it is. What's that, gamma? Give me the gamma.
1.587.
1.1587, okay.
No,
And from-
1.587.
No,
No, that's too
not
big.
right. What's 0.3 divided by 0.5? Oh yeah, it is, sorry, never mind.
Yeah.
My bad, oh, my bad. Okay,
So what I did,
1.587, sorry, my
Yeah.
bad. What's the V?
the velocity is 2.328 times 10 to the 8 meters per second, which is really
2.328?
fast. Yeah, which is really fast.
Okay, so that's pretty darn fast, right? We're like 2/3 of the speed of light. So just so you understand, this is routinely what's happening inside of an electron microscope. Okay, routinely. Okay, so the last question, what was the last question? What is the speed? Oh, we got that. That was the last question. Okay, so are you guys okay? If you didn't
Yes.
get it, no big deal. Just but do try to learn because it's what I'm gonna have to put on the final, right? Now,
So Sean,
yeah.
I originally did joules. Actually, I plugged in joules because and then I got worried because I got the same gamma though. It was really cool because all
Of course
the
you
units
did.
canceled. I had kilograms, meters squared per
Isn't that
second squared,
great?
which is this. Yeah, it was really cool to see.
So
Like, I
what's
got
the
the same
lesson that you
number.
just learned then? What did you learn? Is
I
there more
mostly
than one
learned to
way to solve a
cancel.
problem?
Is you look at the units and you see what you're left with. You see what units cancel and you see what you're left
It
with.
really
There's a lot of
can.
units involved with.
That's a faster way to do it, definitely. Or thinking about the units definitely makes a difference. Okay. So, okay, great. Awesome. Okay, how about the second problem? Or problem 2, rather, the third problem. Repeat for the proton. Should we just, can you guys just,
You don't have to change anything. You just really have to change
the speed?
the mass.
Right.
Once
Okay,
you
so
change
the
the
only
mass,
thing that
you
changed.
can get everything else.
Okay. Okay, so
Because it has the same charge, right? It's just in the
absolutely.
opposite
Yeah.
direction.
Thank you. That's exactly right. So the mass of the proton, did you guys look it up?
Yeah. So in
1.67
megaelectron
times 10 to the minus 27 kilograms.
Okay, cool. And what about, I'm just curious if anybody
MEV,
looked
it's
up the
900 and
MEV.
something, 935.
Okay, so I'm looking on, actually, why am I doing that? Why am I doing that, Sean? Why are you doing that? Okay. Why are you doing that, Sean? Here we go. I'm on Wikipedia. Okay, so I'm looking at Wikipedia and I'm scrolling down and I see the mass. First of all, I see this. This is beautiful. Have we talked about that already? Anybody?
You mean quarks?
Did we talk about quarks in here at all?
I don't think so. We haven't talked
We,
about
we
quarks.
have not talked about quarks, but there's up, down, strange.
Yeah, I mean,
Uh,
okay, I don't think we're gonna, I guess we're not gonna talk about it then. Maybe just, too bad, it's so fun. But anyways, okay, never mind then. Skip it. We can't talk about everything, right? So here's our number, 1.67 times 10 to the minus 27 kilograms. But look right underneath. You see the number in the relativistic format.
938. Yeah.
Okay, so now we can actually just quickly, I'm gonna write that down. So we have, what was the energy? 0.3 MeVs, right, was the kinetic energy. And then we have gamma minus 1 times 938.272, okay, MeVs. Okay, see how it's MeV over c squared. So by multiplying by c squared, we get just the MeVs, okay? So I've written down, this is our kinetic energy, right? This is the
I have a
kinetic-
question.
Yes, sir.
So because the charge is positive, does that mean the kinetic energy is negative?
No, sir, that's actually not what it means. What it means
Okay.
is, okay, what it means is when you write down the change in the electric potential energy, the answer is Q delta V. We derived this last week, right? We talked about this last week. So when the electron is falling. We have a negative charge, right? And then what happens to delta V? Does it go up or down?
Up, I think.
It goes up. It goes to the positive plate, from the negative to the positive. It's a positive change in delta V. So what's the overall change in electrical potential energy, positive or negative?
I never get this straight. I don't know.
Are you gaining or losing potential energy, Christian?
Well, how negative were you? I mean, because a negative and a positive together would be a neutral.
No, they're multiplying each other, Christian.
Right, so it's negative.
It must be. So are you gaining or losing potential energy?
Losing?
That's what negative means, right? If you lose potential, then you gain that much kinetic. So for the proton, what's the difference? The charge is positive, but which way do protons fall?
Towards a negative.
Exactly. So what's our delta V going to be?
Still negative.
It's going to be negative. Well, no, not still. It's the opposite, right? They fall in opposite directions. But you're right. What you meant is the delta EPE is still negative. Exactly. So either way, what happens? You gain or lose potential energy.
That's my bad. Yeah.
No, you're not bad. It's just actually this is the part of learning, man. This is the beautiful part. Honestly, this is why I wanted you to see this, because it's so amazing how perfect it is, right? No matter which way you fall, you're losing potential energy, which means you're gaining kinetic energy. Kinetic energy can never be negative.
I spent so much time on this stuff, I basically like gave up towards the end.
Oh, okay. So everybody good? So you got this? This is our slick method. You could do it a little bit harder with kilograms. It's fine. Actually, I was kind of doing it on purpose that way. Now I just show you this way. Okay. So now you can quickly get gamma. What's our gamma value?
1.000322061.
Okay, 003. What do you notice about the number, right?
It's tiny.
It's incredibly close to 1. So I'm going to guess, yeah, it's not exactly 1, but it's pretty close to 1, that these are pretty much non-relativistic. Okay, so, but let's go ahead and solve it. What's our V? What'd you guys get for a V?
7.578 times 10 to the 6 meters per second.
I got the same.
Yeah, same.
578 times 10 to the 6.
0.02553 times C.
Okay, so basically we're non-relativistic. So actually, this is an interesting idea, right? What was relativistic for the electron doesn't end up being relativistic for the proton, okay? And it's not a big deal, just yeah, but you recognize this. And in fact,
is that because of the mass?
Exactly, because of the mass. The mass of a proton is almost 2,000 times the mass of the electron. I mean, anybody memorize the ratio? I think I memorized 1987, but I don't remember if that's right anymore. It's been a while since I've looked at that. We could just take the ratio. You can take the ratio. Proton mass. Okay, so protons to electron mass ratio. 1836. Okay, well, I thought that maybe it's changed then, because actually it has changed in the 25 years since I first started learning about this. Okay, well, no big deal. It used to be 1987 when I was an undergraduate, so that's wrong. Okay, so let's go with 1836. Okay, that's still almost 2,000 as far as we're concerned. Okay, all right. 1836. Okay, did you memorize that, Tom, or is that the number that you're looking at today? Because when I was a PhD, yeah, so when I was a physics student, my professors made me memorize this. So anyways, you don't have to memorize it, because obviously the number I memorized was wrong now. So, okay, so that was the only change, and we figured out the gamma and we got the V. Okay, great. Okay, now problem number 3, or the fourth problem, we started talking with just before class, And I really didn't give you guys enough preparation for this. So if you didn't solve it, no big deal. But let's talk a little bit about it. So you start off with these masses, and let's call it M1 and M2. And basically, I'm going to solve the last problems, including that bonus problem. Did anybody try to do the bonus problem?
No, I got stuck on 4, and yeah.
Okay.
Before you go on, I took this from a charge perspective and not a mass perspective, and I got a force based on the, I think, what is it called, the Coulomb's law, or the kq squared over r squared, and then I put it to F equals ma, and then I changed it to force times distance equals the kinetic energy equals 1/2 mv squared, and got a force but no velocity.
Okay, so let's just stop for a second, Christian. One of the things that's kind of important, and you remember this, I'm sure, is that what happens to the strength of the force the further you get apart?
It goes away. It lowers as it's in relation to r squared. So it's the same as light.
Yeah, so in other words,
inversely proportional or something like that.
You must do something like this. You must think about, if you want to talk about work, then you actually have to integrate
it.
The work. Yeah, so that's why we didn't do it that way. And we just used the energy approach, because in energy, we don't have to worry about calculus, right?
Yeah.
What you did is fine if the force is constant, but because the forces are changing as we get further apart, you can't actually do it without using calculus.
Yeah.
Gotcha.
Okay, so don't worry, just let's do it right. Let's do it right now, okay? So what are we gonna do right now? When we start, no matter what this distance is going to allow us to calculate the electric potential energy. So we'll say this is the initial electric potential energy. And the formula was K, Q1, Q2 over D, okay? Or actually it's not, let me put R, because that's what
Isn't it R squared?
No, it's not R squared. When you integrate the over R squared, you get an over R. You can derive that for yourself, or if you're interested, work with me and I'll show you how you get it. Okay, but this is the integral of that Coulomb force. Okay, I'll work with you if you want to derive it. But this is the equation that we wrote down. Okay, so this is the potential energy. It goes like 1 over R, and this is the starting potential energy. The charges are the same. They're 2 electrons, right? They're 2 electrons. And so that's fine. What happens when you put a negative and a negative together? What's the electric potential energy? Positive or negative? Positive, that's right. There's going to be a positive potential energy. So what happens as a result of this potential energy? We know that this is kind of our initial picture. The initial picture, right? This is the initial picture. We're taking a snapshot. Energy works from a starting state to a final state, and you don't worry about all the stages in between, right? And so the initial velocities, V1 initial was 0, and V2 initial was 0. They're both 0. Okay, but what's going to happen, right? The final picture, they're going to be really far apart. Actually, I might even say infinity, even though it doesn't really have to be infinity. I'm going to draw them way far apart, right? Really far apart, infinity apart, okay? So if the distance between them is essentially infinite, or just big enough to not care anymore, they are both going to have a velocity. This will be V1 final, and this is going to be V2 final, right? Now, I have actually drawn them to be the same size, but I want to make sure that everybody understands why they must be the same speeds and opposite directions. Or do you already know why? Can anybody tell me why? Why do they have to be the same speeds? What principles do we have? Yes, okay, from conservation of momentum. So not only is energy being conserved, momentum is being conserved as well. So what this means is that when they started, they had momentum, M1, V1 initial, oh man, I keep doing that, plus M2, V2 initial. But because they weren't moving, really, the starting momentum was 0. And that means that the final momentum has to be 0 too. But what is the final momentum? It's the mass of the first particle times its final velocity plus the mass of the second particle times its final velocity. Okay. So how do you get 0 if you add two things together? There's only one way. One of the quantities is a positive and the other is a negative. There's no way. Oh yeah, they could be both 0. Okay, Tom, smart aleck. But they can't be both 0. Thank you for that comment. That's great. So one is positive and one is negative, right? And really the key part is momentum is a vector and velocity is a vector. So when we look at the directions of the velocities, because they're recoiling from each other, we would call this one positive probably, right? That would be the standard way to describe it. That's a positive velocity. And this one is negative. And so that's actually why you get a negative momentum. Oh, I did it backwards, right? Negative and positive. Sorry about that. Because V1 is flying backwards, okay? And they must be the same. Now, in this particular problem, because they're both electrons, right? Then when you solve this, you put this thing over here and you put negative M1 V1 final equals M2 V2 final, but you can actually divide both sides by M1 and the masses are going to be the same. So in fact, they cancel on both sides. So we just found out that V2 is negative of V1, okay? But when we're talking about kinetic energy, oh, sorry, let me go back to the, now we're ready to finish the problem. We're ready to finish the problem. These are both moving the same speed, okay? And now we would invoke conservation of energy. Okay, so your starting energy equals your final energy. And when we started, what kind of energy did we have? We had the electrical potential energy. And when we're done, we have two kinetic energies. We have kinetic energy 1 and we have kinetic energy 2. But in fact, if they're moving the same speed and they're the same mass, they're the same kinetic energies. So basically you get two of these final kinetic energies. So remember that because kinetic energy is squared, velocity squared, assuming it's not relativistic.
Oh, that's why.
It could be relativistic. Is it relativistic? Did you guys get an answer that was relativistic?
No, not at all.
Okay, if it was, it wouldn't be a problem. You just put in the relativity here, put in the formula for gamma, and then you could find our solution. Okay, so we got the basic idea. So help me out here. What did you guys find out? What was the final velocity?
Well,
Final
I
speed?
used the equation, the square root of 2 kinetic energy divided by the mass, but I don't know if that's right.
That's how you do it. Sure.
Square
Yeah,
root
assuming
of
it's non-relativistic. What'd you get?
times. So I got 711 meters per second, which is a very small number.
It is kind of small. Anybody else agree?
I got 502. It's close, but different.
Yeah, those
Yeah,
are.
that's
Are we,
those are
wait, which one are we talking about? We're talking about number 3, right?
Yeah.
Oh, we should go back to what the force we got. We didn't talk about the forces that we got.
No, you
for
don't need
the-
the forces.
The
We don't need
Q1,
forces.
Q2 for finding the kinetic energy though.
No, you don't
No,
need
he
forces.
covered that initially. That's the way I did. I was wrong.
Yeah. So you want to use the potential energy actually.
Yeah, the KQ1, Q2 over R.
Yeah.
Yeah, that's so we should talk about what number we got there.
Oh, okay. Maybe we should. That's a good idea.
Yeah,
So we got
we should.
8.99 times 10 to the 9th. We got 1.602 times 10 to
Right.
the 19th
And that's just
squared because
squared.
it's
Yep,
times
yep.
itself, right? Divided by 1
Divided
millimeter.
by 1 times
10 to the minus
-3.
third meters.
Yeah.
Okay, I don't need the meters. Okay, those are our
Exactly.
numbers. Okay, so who got? Give me a number. What's the number?
I mean, I got 2.307 times 10 to the negative 25.
Sorry, just one more. 2.3307.
307.
Okay, so
yeah, what Tom
307
said.
times 10 to the
Negative 25.
10 to the negative 25. That would be joules. Okay, it looks like we got just
Yeah.
joules. Come on, Tom. Joules.
But he's putting out all the units, which is yeah.
But it's joules. It's joules. Okay, we're just gonna joules.
Why do I see
We're
C?
done, joules. Okay, thank you. Okay, and now, so what did we say? That this electrical potential energy ends up being split in half. So one electron gets half of it, and the other electron gets the other half. So 2 times their final kinetic energy. So the kinetic energy is going to be half this number. So 1 point, I should have left it as well, whatever. Okay, 1.151
Yeah, 1.5.
4, okay, times 10 to the negative 25th. And then Kenny's your formula, right? Ke equals 1/2 mv squared. So V equals 2 Ke over m, take the square root. Okay, I'm good with that. Okay, so what was our, we got a, okay, someone got 503. I'm not going to argue about 502, 503, but they seem to agree. Okay, Kenny? Who gave me the 711?
I don't know
Was that-
what I did. I did a calculation wrong or something. I don't know.
Okay,
I got a feeling that maybe, did you remember to take half of the EPE to figure out the KE?
Yeah, I think that's where I just didn't do that. I just didn't do the half.
oh, maybe
the
that's
half.
what happened.
Yeah.
Yeah,
that's probably
that could
what happened.
be, that would actually work out, right? Square root of 2.
Yeah.
502 times the square root of 2. Yeah, that's what you did, buddy. Okay. So this was the tiny little thing. You forgot that you had to cut it in half. Okay. Good? Yeah, that
Yeah,
explains it. Okay. So we're going to say that that was our answer because this one is 503 whatever times the square root of 2, right? And that's exactly because, yeah, anyways. All right. Because the KE that he used was just a little bit bigger. Okay, good. So how about the protons? Anybody do it for the protons? It's the same problem, right? Really the same problem. I said repeat it for a proton, right? Oh, no, I didn't. Did I? Just never, I didn't. Oh yeah, repeat for protons, 1 millimeter. Okay.
You
So
did
how's
for 4.
What's the problem? There's a tiny little difference, just a little tiny difference. What'd you get? So for the protons, the final speed was 11.8. Anybody else get that answer? Pretty slow, by the way. Kind of boring.
Yeah,
but
that's
okay.
what I got just right
Okay,
now.
check. Okay, good. And
I
now
took
the
my
last
answer.
problem, the bonus problem is just kind of a fun thing, just to understand, slightly unequal situations. This one, the speeds will not be the same, right? So for the final problem, number 5, okay, so I like number 5. I think it's kind of like wraps everything up and shows you one more little tiny little, challenge, right? In this one, we have the mass of an alpha particle. The mass of the alpha particle is 6.644 10 to the minus 27. It's almost 4 times as massive as a proton, right? 1.67 something. I forgot the numbers. Okay. And it has a charge Q of positive 2 elementary charges. Okay. So it's a little bit different. And but if you think about that, okay, you got a speed of 21, Tom, or 11.8? Tom, who wrote? That's Tom, right? Why did you write 21 meters per second? Sorry, I don't know why you wrote that. Anybody? Oh, for the current problem. Okay, he's giving it. Oh, never mind. Okay, I got you.
Yeah, I got the
Okay,
same
he's
thing.
giving us an answer, but I just want to work through with the people that didn't get this before. 1.67 times 10 to the minus 27. The idea is that you need to think about the fact that when these 2 particles separate, they're not the same masses, right? The alpha particle is much more massive than the proton is. So the mass of the alpha particle, the mass of the proton are not the same. So when they recoil from each other, right, when they fly apart, and also the charges, right, this is positive 1 elementary charge, it's positive 2 elementary charges, we have a different amount of starting energy as well. Okay, so who's going to be moving faster when they're flying apart, when they're finally very far apart from each other?
The mass of the proton.
The proton, right? The smaller mass proton has to have a much higher final velocity, than the alpha particle. Okay. Oop, V2 final, sorry, V2 final, V1 final, V1 final, okay. So the proton is faster. Okay, so starting off, what's the initial potential energy? It's K Q1 Q2 over R. So how does it compare to the problem? What did I make the distance? Some random distance. Oh, 1 millimeter. Okay, it's the same thing. Okay, so actually, in fact, it saves us a little bit of time. How is this going to be related to the problem that we just did a few minutes ago? The only difference is we have 2E and E over R, which means it's exactly twice as much kinetic energy as we had in the previous problem, twice as much potential energy. So the potential energy that we had was right here. It's going to be twice as much, right? So it's going to be 4.614, 10 to the minus 25th. Okay, everybody get that? And then the hard part, this is the harder part, is just, it's not that hard either, but to think about what happens to the kinetic energies now. Are the kinetic energies going to be equally split now? Who's going to have more kinetic energy? This is a little tricky. Actually, you don't just immediately come to a conclusion. In fact, maybe it would be worth just describing this situation for a moment, right? How do two particles fly apart? How does their kinetic energy compare if they are not the same mass, right? So this is actually a really kind of interesting situation that often happens in physics. Two objects are repelling each other, right? When they finish, how do the kinetic energies compare?
I would feel like it would be the same, but
yeah, but I want you to understand why that's not going to be the case. Okay. So you need to know that they're not the same. They are not the same. Okay. So what is the same? Well, when you started, the initial momentum was 0 because they weren't moving. And when you're done, the final momentum is also 0. But what does it mean? This particle, M1 times V1 final plus M2 times V2 final has to add up to 0. They have to be 0. So if you solve this, you get that, let me bring this one over here. V1 final, M1 V1 final equals negative M2 V2 final. I just did the opposite of what I did last time. Divide both sides by M1. So we find out V1 final equals negative, I'm going to put this ratio here, M2 over M1 times V2 final. So this particle is going to have a negative velocity compared to V2 final, and the ratio M2 over M1 is how fast it's going to be going. So if in our story, this one was about 4 times, right? M2, about 4 times in our story. And so maybe I'll just use that as an example, right? You would get M2 over 4M2, it's going about 1/4 the speed. Okay, 1/4 the speed, right? So what about the kinetic energy? Kinetic energy of particle 1 final is 1/2 the mass of 1 times the final speed of 1 squared. The final energy of particle 2 is 1/2 M2 times V2 final squared, right? So if I know the ratio of the two masses, I can actually compare their kinetic energies to each other, right? If I know their ratios, okay? So actually, before I do all that though, let's go ahead and put something, let's put this in right here. Put this in right here. Let's put this in to this formula. So we have 1/2 M1 times, yeah, so Tom is saying V matters more, right? So whatever happens to V is going to be a bigger impact. So negative M2 over M1 V2 final squared, right? The negative is going to go away because you're squaring a negative number. You get 1/2 M1, and now I'm going to multiply, square this out. So M2 squared over M1 squared V2 final squared. And I could cancel one of the m's right here. And so I get 1/2 m2 squared over m1 V2 final squared. You guys read that? I can't even read that. Let me write it one more time. 1/2 m2 squared over m1 V2 final squared. So look at this number here. And so we're going to compare these two here, right? So how do these compare? Well, actually, this is in here and this is in here. So let me just write this out. Let's write m2 over m1 times 1/2 m2 V2 final squared. And this is the same thing as this kinetic energy here. So we actually figured out something, that the kinetic energy of the first particle is exactly m2 over m1, whatever that ratio is, times the kinetic energy of the second particle. So because m2 is a smaller particle, like only, the proton, and m1 is 4 times that, the kinetic energy of the alpha particle is going to be about 1/4 the kinetic energy of the proton. Okay, so let's use this result to solve our problem. Okay. So you have the initial potential energy, and we know what that is. But now we're going to have the kinetic energy of the alpha particle plus the kinetic energy of the proton, right? And we derived a little formula for the kinetic energy of the alpha particle, right? We said that it's going to be the mass of the proton divided by the mass of the alpha particle times the kinetic energy of the proton. Okay, so that's going to be this right here, plus the kinetic energy of the proton. And so we can factor out the kinetic energy of the proton, right? The kinetic energy of the proton times this ratio plus 1 is going to equal the electrical potential energy. Okay, so that's a little bit of work, and I agree this was a hard problem. Actually, this was optional. If you didn't do it, no big deal. But I think it's kind of a cool problem to also show you how the math works. And so you would solve for the kinetic energy of the proton, and then once you know that, you can put it in here to find the kinetic energy of the alpha particle. Okay, so divide by this ratio plus 1, divide by this ratio plus 1. You can find the kinetic energy of the alpha particle. Once you find the kinetic energy of the alpha particle, you find the speed of the alpha particle. Like Kenny told us, 2 times KE divided by the mass of the proton, right? And then once you know this kinetic energy of the proton, you can go back up and figure out the kinetic energy of the alpha particle. The kinetic energy of the alpha particle is going to be this ratio times the kinetic energy of the proton. And so once you find that, the speed of the alpha particle is going to be 2 times the kinetic energy of the alpha particle divided by the mass of the alpha particle. Okay, so Tom gave us some numbers, Tom, 21 meters per second was the proton. That's Tom. And what about the alpha particle? And I'm wondering if anybody else has gotten this. 5.3. Okay, and if you notice, that's pretty close to 1/4 the speed, right? Very, very close to 1/4. So looks pretty good just on first. Wait a second. Yeah, of course, that's right. That's funny. The kinetic energy is 1/4. Something's wrong. Why is that right? I think I messed something up. Anybody see what I made a mistake? I think I made a mistake. Oh, no, that's fine. Okay, it is 1/4. Okay, because the mass, no, that's good. No, it's good. It's good. It's right. Okay, this is good. Okay, so actually, speed. Okay, so just to go back a step, which one's more important for kinetic energy? well, speed is, right? But if you remember, mass 1 was 4 times as massive, but the speed is 1/4, right? So what's 4 times 1/4? Well, one of these 1/4s will go away when you multiply by 4, and you end up with just that 1/4. So it's good. Everything's good. Okay. So can anybody confirm those answers?
Yeah, I
if
got the
not,
same answers. Yeah, I
you
got the
good.
same.
Okay, great, cool, excellent. Okay, all right. So we solved our homework. Should we try to go on to something new now? Whoa, what's that problem? I don't know what that is. Let's learn something new. Okay.
Yes.
So I actually, this is huge, and obviously I can't do all of it. And I started to think about that. You know, actually there's just so many things, but we're not going to study like electricity, like a standard electricity discussion. We're not going to do that, you know, because there's just not enough time to do everything. But I want to apply this to astrophysics. So let's go ahead and try to see the ways in which this might apply to astrophysics. So let's go ahead and look at this. If you guys are looking at April 24th on Canvas, you can see all of these links that I put in here. And again, I actually put this one last, and I'm like, why am I putting that last? It's probably the most important part of what I want to show you. So I made it first. So here are the questions, motivating questions. How are magnetic fields produced in planets, stars, neutron stars, black holes? Because all of them can show evidence of a magnetic field, right? And this is a really neat idea. I mean, I could teach a whole course on this, literally. Actually, I could imagine teaching a whole course on magnetic fields of interesting things and the sun and how that works. Oh my gosh, it's just endless. But let's go ahead and just click this link and go to something called Hyperwall. Click that link. Okay, here we go. I think I've already got it up actually. Okay, I'll just show you again. This is the Crab Nebula. And by the way, it's got a really cool story. So before we look at this picture, let's just read this little description. Okay, the Crab Nebula, Messier 1, Charles Messier's list of objects is number 1, is the remnant of a supernova that exploded in the year 1054. Now, that sounds pretty precise. And I don't know about you guys, but most of the time in astronomy, when you say something happened, you usually give quite a little bit of leeway about the, you know, the timing. But you'll notice that they're very specific, the year 1054, because it turns out somebody wrote down what they saw. There was a mysterious new star. They called it a guest star. And what this means is there was actually a new star in the constellation of Taurus. It wasn't Taurus for the Chinese astronomers, but we identify it as Taurus today. And this star was visible during the daytime for about 3 weeks. So it was really special. You and I have never seen this. You've never seen, except for our sun, you've never seen a star during the daytime, okay, when the sun was up. But this one was visible during the day, and then for about 2 years afterwards. But the reason they were able to identify that is they found this cloud that we call the Crab Nebula. They thought it looked like a crab, and you'll see a picture a little bit later. It does kind of look like maybe a shell of a crab. And what was more important is as they watched it, they discovered that it was getting bigger. It was expanding. And so this is a really wonderful story to tell, because if you see something getting bigger, you might stop and ask, well, it's getting bigger, maybe it had a beginning, right? When was the beginning? And you try to imagine playing the movie in reverse, right? If you can calculate the rate that it's expanding, you could start to work backwards and ask the question, well, when did it originate? When was the cloud really small, right? At that smallest point, when did that occur? And it turns out they got somewhere in the year, in the millennia, in the century 1000, and they went looking through the record, the astronomical record, and then discovered that in the year 1054, there was this special event. And it was exactly the right location. So if you go to the center, right, the location of that guest star is right where this cloud was located. Okay, so I'm going to start playing it, and I'm going to make it bigger. This is slow motion, but if you look, actually, I guess I need to pause. If you look at the bottom, it shows you the kind of light we're looking at. These are radio waves. And the telescope that produced it, okay, the very large array, it's an array of radio telescopes. And the red color is a false color, of course, because we can't see radio waves. Okay, and now we're going to jump to the infrared. Again, false color because we can't see infrared. And so this is from the Spitzer Space Telescope. And you can kind of notice that you still see that big cloud shape. Here is optical, and you notice it's getting sharper. Anybody remember why it's getting sharper? What's going on if you, I'll just pause for a moment, actually. Why is it getting sharper? Anybody remember why? What's the reason? Yeah, it is incredible. It's absolutely beautiful. Did I just stop the share? I did, darn it. Okay, go back to it. Let's go back. Okay, anybody remember why? Because the resolution depends on wavelength, okay? So smaller wavelength, the sharper resolution. Okay, this is ultraviolet. You still see a cloud. And the last image is the one that I just find so interesting. This is an X-ray picture taken with the Chandra telescope, space telescope. And I want you to notice something really special. There is a very sharp point in the middle. There is a disk around it. And does anybody see jets? Okay, because that's what I want to talk about today. There's a really awesome thing here. You are literally seeing that this object in the center of the cloud has a profound and powerful magnetic field. Okay, and you only see that when you look in the X-ray part of the spectrum. So this is a composite showing everything together, and it's just an amazing thing, right? It's a wonderful thing. Let's study this, right? What's going on? And it's just rich. It's got so much stuff. First of all, it is a supernova. That in itself is awesome, an exploded star. But really today, my topic is for you that I want to explain some of the features that we see in the Crab Nebula. They are magnetic. They are magnetic features. Okay, let me look at the chat. I can't look at the chat when I'm sharing screen. Okay, that's a fail. Okay, so we'll just
speaking of things in the sky, I was out on a walk last night, and I saw what I initially thought was what we would call a shooting star, or an object entering the atmosphere, but it actually turned into a bolide, a fireball. It ended up slowing down, turning red, and then dissipating, and it was amazing. It lasted for probably a second and a half, and
wow,
or longer. Was
there a flash?
No, there was a flash during the high winds that probably was attributed to a transformer nearby, because after that, like, there were a bunch of cops and fire trucks and stuff. But but maybe 20 minutes before that was when I saw the bolide, and it was incredible. I hadn't seen anything like it before.
That is
I
awesome.
probably never will again.
Oh yes, you will. Sure you will. Come on, you got a lot of years to live. If you look for them, Christian, you're going to see them. But actually, Lonnie pointed out there is actually a meteor shower going on right now. And
it peaked 2 days ago. I didn't expect to see anything.
Oh yeah, no, it lasts for a couple of days. That's awesome, dude. That's great. So yeah, fireballs are kind of rare. There's something called the Fireball Network, and they actually find them every single day around the Earth. They're somewhere on the Earth. There's actually a network of cameras that are looking for them, and then they try.
That's amazing.
Isn't it? It's amazing. Yeah. So they try to figure out where they're going to land, because then people go looking for the fresh debris and the fresh meteorites, and it's a very exciting thing to do. I would love to do that myself one day. In fact, I think that should be an astronomy club activity at some point.
That's epic. Yeah.
Wouldn't that be fun to go to the desert and try to find some real meteorites? Okay, that is a tangent. You guys got me on a tangent. That's awesome. Okay, great story. But the Crab Nebula is just a really interesting thing. And so that's going to try to motivate you. So the thing that you wanted to notice, and this is actually really, really cool, is that in the middle, I'm turning it sideways just because, I don't know, I have a preference for up, down. But what you might have noticed is there's a jet coming out of the top. And actually, it was a little harder to see, but there were 2 jets And this is a sign of a magnetic field. And actually, it's probably a little bit beyond our course to really figure out how, what the strength of the magnetic field is precisely. But if you remember, we saw that in the X-ray. It was an X-ray image, right? So these are high energy photons that are being created. This is actually a very high energy kind of situation. So the two is kind of important, right? So we want to talk about magnetism. What is magnetism, right? Magnetism, right? Magnetism. What do you guys know about magnetism? Anybody know anything about magnetism? Magnets? Magnet. What's a magnet?
Neodymium magnets are super strong.
Okay, you can, what was it?
I just know that neodymium magnets are like super strong.
Oh, yeah, that's true. So, but if you have a regular magnet, you might remember that there's two ends to it. There's a normal little magnet. And yeah, lodestone, very good. So actually, once upon a time, they found these natural magnets. But either way, every magnet, if you study it carefully, has two ends. And one end is called the North Pole, and the other end is called the South Pole. And that's interesting, right? So, but why is it called the North Pole? Well, the answer is, you guys know why, because these lodestones were kind of special. If you took them, and you floated them, like you put it on a leaf or something and put it in a bowl of water, on some kind of a leaf so it floated, then what was really amazing is one end would always point towards north. Okay, a piece of cork, yeah, it could be almost anything. First you had to finish your wine. Okay, we got a joker in the audience here. Okay, so this is called the North Pole, right? And so the part that's kind of critical, I'm your teacher, I want to teach you something really kind of critical, and it's kind of amazing to me, and it wasn't something that's very intuitive. There's always two poles for a magnetic field. And maybe at first, when you look at this, you might also remember, something about magnets. What happens if you try to put two magnets together, right? What happens if you put two magnets together? Do they stick or do they repel?
Depends which sides are facing each other.
Thank you. Exactly. Right. Depends, right? And so what if you put a North Pole next to another North Pole? What happens?
They repel.
They repel, right? And if you put north next to a south, they attract, right? Okay, so that's cute. And so when you think about that, there's kind of like, there's two ends of a magnet. And then a lot of people say, hey, there's two charges, and there's positive and there's negative. And one of the real problems that I find is that sometimes students will think these are the same, and they're not. They're not the same, okay? So what's different? What's different about electricity and magnetism? I mean, they're the same in terms of attraction, right? Positive repel other positive, negative repels other negative, and positive attracts other negative. That's true, right? That's
magnetism has no charge to it.
Well, that's what, okay, great. So what does that mean, Christian?
Yeah. Well, you said what's the difference?
Right, yeah, okay. Okay, so you're being very concise. You're too concise. Can you be a little more verbose?
The charges can't exist on their own.
Thank you, okay. All right, so, and Tom is writing it too. So you can have a positive charge all by itself, and you can have a negative charge all by itself, but you cannot have a North Pole all by itself or a South Pole all by itself. That cannot exist. They're not possible. And you can say, well, why not? You know, that should be possible. Yeah, Tom gave us the name. These are called monopoles. Okay, there are no magnetic monopoles. There are pseudo magnetic monopoles. And pseudo means what? Fake, thank you. And it means they act like monopoles. Well, that's actually pretty cool. Well, why aren't they monopoles? Because they're really not monopoles. You cannot actually make it. So if you take a magnet, here's the idea. If you take a magnet with a north and a south, and you chop it in half, right, to kind of separate them, you don't get that. What do you get? What do you get? You get a north, and you get a new south, and you get a south, and you get a new north. You make two mini magnets. You cannot separate north from south. So they are somehow connected together always, right? They're always connected together. And so that's kind of an interesting idea. Actually, I didn't want to talk about it too much, but I do want to just show you. I mean, I'm not going to, I can't do this, but there is a fellow named Maxwell, and Maxwell is the same fellow who figured out that light is an electromagnetic wave. And there's something called Maxwell's equations. I was not going to do this, but I just feel an intense need to do this. So don't worry, and we can't cover that in this class anyways. It's too much, but I'm gonna just show you something. There's different versions of it, and I actually this is a version I wanted to talk about, I guess, or this version. This one's a little easier maybe to look at. There's an equation. There's a set of equations, and actually I don't know that it means anything to anybody yet. So actually some of you maybe, some of you, okay. But just look at the first two equations right here. These first two equations. Okay. Actually write them down. Let's write them down. What does it mean? What does this mean? Actually, I don't know why I'm telling you to write this down. It's just letters on a page. What the heck does it even mean? What does it even mean? Well, so I want to actually just, again, why am I doing this? I don't know why. Okay, just look at the first two equations, okay? This actually says electric fields come from charges, and magnetic fields cannot come from, there's no such thing as a magnetic monopole. There's no places for a magnetic field to come from, right? So this term, yeah, vector calculus, we're not going to do it. We're not, I know, I promise. But these are called divergence. This term, divergence. You write that word down. That's what we see right here. It's called the divergence. So the divergence of the electric field means what? Well, it's zero when there's no charges. This rho is the charge density. So if there's no charges, there's no electric fields. When there is charges, then what happens, right? If it's a positive charge, we learned that the electric field points away from it, right? It points away from it. Right? Electric field points away from it. That's a positive divergence because the electric field lines go away from it. And for a negatively charged particle, the electric field goes towards it. That's a negative divergence, right? So another word, and you don't have to really know this, is that we say that a positive charge is a source of electric field, right? It's a source. And this one where the lines are going in, the arrows are going in, it's called a sink. Yeah, these are Greek. Oh, you're funny. So this is another thing. It's kind of like water, right? Actually, in fact, these equations for electric field follow equations for the flow of fluids, right? Fluid dynamics. They obey those equations too. So if this were water, this would be a faucet, right? Water coming out of the faucet. And this would be the hole where the water goes. This would be the sink. This would be the drain, right? There, I couldn't think about the word. Okay, that would be the drain. And so this equation says, yes, electric fields come from charged particles. But this equation says you can't have a magnetic field. Sorry, this is magnetic field, sorry. Why? Okay, don't worry about that. I could tell you, but then I'd have to make the course a lot longer. Okay. This is the magnetic field symbol. So B, you're like, why B? Why not M? Well, the M is used for something else, so that's why. But also the reason is because it comes from an A field. Okay, so that's actually the real reason. Okay, so magnetic field is B, and there are no sources or sinks. No magnetic monopoles. So I would like you to learn this, even if we're not doing any of this work, just to understand that in our universe, we have never observed a magnetic monopole. We have never seen magnetic field come from someplace or go into someplace like this. It just never happens, which means that magnetic field is a loop of some kind. It's always a loop, right? It makes loop. Tom, I don't know the answer. Grand unified theories predict them. They could, probably some theories do. I don't know. Actually, I don't want to blow your mind actually, but I do want to blow your mind a little bit. But let's go back to basics. Okay. So magnetic field is going to be some kind of a loop, it turns out. So actually, I guess I do want to tell you something. In fact, so put this in your notes. I want you to know this. I want you to know this, okay? That if you have a north magnetic pole and a south magnetic pole, the magnetic field looks like something that I can define, right? This is actually the definition of a north pole. It seems to come out of the North Pole and it loops around to the South Pole. What I'm not telling you is it has to continue inside of the material. And so the direction of the magnetic field appears to come out of the North Pole and come into the South Pole, which seems to be, didn't I just tell you it can't do this? You can do it if they're together. You can do it if they're together. And so this, yeah, I think I probably shouldn't have just told you any of this, but okay. So the magnetic field direction is out of a North Pole and into the South Pole. But remember, I'm not telling you that the way that it really works is these continue inside, okay? So these are the magnetic field near a magnet, a permanent magnet. It's called a permanent magnet. But it's not really permanent, but anyways. Okay, so I have too many things to do and I think I'm going too slow. Let me go ahead and jump to this activity right here. Okay, so there is the next link. The next link in our list is PHET. I love you, PHET, you're awesome. PHET. So here it is, PHET. You click on the link, it takes you to PHET. This is a Java applet. I know Java is unsafe and is going away, but if you get it from here, I want to say that I think I would be willing to bet my reputation on the fact that it's safe for you to run. And I want to run it. I'm going to run it. I don't care. I'm going to run it. And so I'm running it, and you don't have to run it, I guess. Okay. So the goal is to understand something about magnetism from this application. And so here is the application. Here's what you see, okay? So this is a compass, right? Here's a compass, and the compass has a needle on it and in it. And you may never have noticed, but if you did pay attention, you probably noticed that one end of the compass needle is shaded, right? Often it's red, and that is the part that points towards the north. And the reason it is pointing north in the Earth, well, actually, sorry, I got ahead of myself. So that's the north magnetic pole. So a compass needle, the red is attracted to this end because this is a north magnetic pole. If I put the compass over here, you can see that the red is repelled and the white is attracted because that's a south magnetic pole. So a compass needle works because, in fact, it is a small magnet. And so you can see that at different places it has. So this is how I drew that picture for you just a minute ago, right? So the arrow comes out of, So basically, the direction of the magnetic field is whichever direction the needle of a compass is pointing, right? So as I come over here, it points out like this, and I come over here, it's curving, it's horizontal right here, pretty close, curving towards, right? So the direction of the arrows is the direction that the red is pointing, okay? So here's a really awesome idea. Electricity can create magnetic fields, and it does. So the flow of electricity, this is a battery, right? Turn it down to nothing. There's no, so these little dots are showing you the flow of electrons. If you remember, this is a copper top. So actually, those of you who know what a Duracell battery is, you recognize it. You could probably identify which end is positive in this picture. Anybody I could recognize? This is the positive. The little nub is a positive. So if I turn on voltage, which way do the electrons go? And the answer is the battery makes the electrons go towards the positive, right? That's actually, we're not studying that, but that's how electricity works. It's kind of like the electrons are falling in the wire, right? They're falling in the wire. Okay, so at this point, I forgot that I was going to do something. Yes, Tom, that's right. I wanted to tell you guys that if you want to play with me on the PS4, sometimes my name is right hand rule. Okay, because I think this is one of my favorite things in physics. Okay. Okay, isn't that relevant? Okay, so take your right hand, raise your right hand. I promise that I will learn as much as I can learn. Okay, so actually I need to turn the camera towards me. Okay, this may be weird because I may be flipped over. Oh, crud. Okay, oh well, okay, this is my right hand. Does it look like a right hand to you? Oh, well, anyways, you guys, this is my right hand. Raise your right hand. Okay, follow. I solemnly swear to study physics for the rest of my life. Okay, here we go. There's some right hand rules, and one of them is there's a bunch. There's three. You don't need to learn them. I don't know why I'm doing this, but it's just for completeness. They're going to be super fast. Okay, so super fast. So number one is the right hand rule. When you're near a wire that has electricity in it, there is a magnetic field near it. Okay. And so it's called the right hand rule. So what you're going to do is I'm going to show you in a moment a wire, a vertical wire. And it's important to know that the electric charge, the electric current, I really didn't want to do this. Why am I doing this? Oh man, shoot. Does anybody know why I'm having a hard time?
No.
No. Do you know what electricity is? So you guys know more
The
than
flow of electrons.
the flow of electrons. Okay. But Benjamin Franklin, thank you very much, did not know that electrons were the thing that were moving inside of the wires. And he hypothesized that there were these positive charge carriers, and they are moving inside of the wire. So he invented, much of the beginning framework of electricity, and he described the flow of positive charges. And so we usually use, even if it's not really happening, the flow of positive charges. It turns out it doesn't matter, but the rule that I'm about to teach you is the rule for positive charges. I know it's like so backwards, but it doesn't matter. It's still my favorite rule. How do you do the rule for negative charges? It's called the left-hand rule. Or you just flip the answer over, okay? All right, so I guess I need to tell you this. All right, I apologize. I feel like some of you are like, I didn't need to learn this, but I just want to teach you. And I think this is very beautiful. So just bear with me for one moment. We're going to be very quick, okay? Electron, that's the Greek word for amber. How cool is that? Okay, so we're going to go ahead, and I do want to make sure you understand that if you decide to learn about electric current, we will usually pretend that there are positive charges flowing or moving, right? Okay, we pretend, okay. And so I'm going to draw a big wire for you. This is a big wire. This is a big wire. And I want to put the current is going up. And the symbol for current, the symbol that we use is capital I, okay, or I, just whatever, I. So there's my current. So this is positive charges. What's really happening most of the time when the electricity is flowing is, if this is a positive charge, what would make it go this way? And the answer is, if you connect it to a battery. Why are you doing this? Why? Why are you doing this? Why? What would make positive charges want to go up? Which end of the battery is this connected to? And the answer is the negative side. Okay, that's the negative side. And so if that's the case, the positive side is down here, which gives us the positive charges. They flow up, they fall up towards the negative terminal. But that's actually not what's happening. The real electrons fall which direction? Well, they're negative, and they fall this way towards the positive. So the real electron current is always just opposite of this fictitious positive current. Okay, so you understand, I'm trying to show you something that I thought was simple, and it would have been simple if I just ignored this, but I don't want to just ignore it. I want you to actually know the truth, okay? Yes, Tom, holes are real. Okay, but they're not typical. Okay, so if you guys want to go further in physics, Tom just mentioned a word that I want to, you could go ahead and understand. A hole is it's found in a semiconductor. And what is it? It's a missing electron. That's what it is. A hole is a place where there was an electron, but somehow it's not there anymore. And those holes, the missing electrons, will appear to move, and they are positive charges. If you analyze it carefully, you'll find out that it's really the electrons that are moving in there as well, right? Only the electrons are movable inside of material, but they act like positive charge carriers. So in fact, inside of solid material, it's the electrons that move, not the positive charges. The positive charges are kind of stuck. So, but I don't want to lie. I do want you to be aware that, in fact, there are cases in chemistry, especially. In chemistry, you can have the flow of positive or negative ions, and that's fine, okay? And probably the same thing is true inside of stars, okay, or other things, okay? Okay, so back to the story. Okay, after wasting your time, I'm sorry. Okay, so right-hand rule number 1 is the magnetic field near a wire, okay? Yeah, that's exactly right. The hole seems to move backwards because it acts like a positive charge, because the space where the electron is moving because the electrons are filling it, right? So a migration of a hole is really from the electron flow. Yes, it's always the opposite. So positive charges, opposite of negative charges, always. Okay, so here we go. Right-hand rule number 1, super simple. Here it is, a wire, and you use your right hand, and you grab the wire so that your thumb is pointed the direction of the positive flow. And your fingers wrap around the wire and indicate the direction of your fingers is the direction of the magnetic field. But the key thing is the magnetic field makes little circles around the wire. Isn't that cool? Okay. So back to our picture on the paper. You want to draw me a picture if you can. Okay. Near this wire, the magnetic field is going to wrap around the wire, wrap around the wire like this. And the direction is going to be like this. So I'm going to put an arrow showing that the arrow is wrapping around in this direction. This is the magnetic field, right? It follows the first right-hand rule. Okay. All right. First right-hand rule. Right-hand rule number 2. And again, why am I doing this? Just because I'm your teacher. No other reason. Sorry about that. A loop. A loop. This is actually a little bit redundant. A loop of wire with current flowing acts like a small magnet. Acts like a magnet. Could be big actually. Okay, acts like a magnet. Okay, and so if I have a loop of wire, a loop, and I have current flowing in this direction. This is positive current. Okay. Then I'm going to use my second right-hand rule a little bit differently. Okay, so I'm going to show you my right hand again. Okay, so this time you're going to use your fingers to represent the direction of the current. So I'm going to curl my fingers the way that the loop current is going. And there's only 2 ways to do it, right? If the loop is here, I either curl my fingers like this or I curl them like this. And the direction of my thumb is the direction of the magnetic field. Okay, so I'll just show you how that works. Okay, so if I curl my fingers like this, then the magnetic field points up like this, which means if you interpret it, it's like this is a North Pole and the South Pole is on the bottom, right? Because the magnetic field points away from the North Pole. It does in fact loop around, don't forget that, right? But we're just worried about the direction here. So basically this thing acts like this little magnet right here. Okay, so I've done the second. They are amazing. Yes, they are amazing. Okay, so we are going to go back to our little app here. And I want to see if you guys can do this with me. So if you notice the current right here, it's already showing you the answer, but the current is flowing, it's going up this wire, which would mean what? These are negatively charged particles. Which way would the current go if this was a positive charge? They would go down this wire, down, right? So if you try to curl your fingers so that they go down and around, what direction is your thumb pointing? Towards the right or toward the left? Which way? Just say it out loud if you can. Can you say it?
To the right.
To the right is correct. Okay. So watch, and you can see the arrow is pointing to the right. So when you put this compass near it, it acts like this is the North Pole right here. What happens if you turn off the current? It's gone, right? What happens if you flip the direction, right? Then, in fact, the compass needle changes as well, okay? All right, so that is a really cool idea, okay? So finally, I want you to know something important, right? That the Earth has a magnetic field, which is more complicated than this, but a simple interpretation is that there is electric charge flowing inside of the Earth somehow. And we have a name for this. It's called the dynamo effect. And in fact, it's the only mechanism that I understand for generating magnetic field. It's the only thing I can think about. It's electric current, just like we saw here, except it's not going to be quite as simple. And so this is the Earth, right? And so you can see the United States is here because we're on top, right? No, I'm just kidding. But anyways, the inventor of direction, you know, lived in the Northern Hemisphere. And so this became the top, right? This is the North Pole up here. So the North Pole of the Earth is what kind of magnetic pole? Tom told you a few minutes ago, right? It is a south magnetic pole. That's why the North Pole of a magnet points towards it, right? So anyways, you can see something interesting. The strength of the magnetic field is how bright these little compass needles are. What do you notice? Where's the magnetic field the strongest? Where is it brightest? Okay. Can somebody just tell me what Tom said? Or whoever said it. Okay, nobody's talking. Okay, the answer is near the poles. Okay, all the people talking, everybody's saying pole. Okay, I can't hear you when I do that darn thing. Okay, so the answer is it's strongest near the poles. You see where it's brightest, and it's weak when you go over here and over here. It just gets weaker the further away you get. Okay, so anyways, that's interesting. Okay, great. That's interesting. Okay, so that's our second right-hand rule, and I'm going to now show you the third right-hand rule. Okay, but before I do, I'm actually going to tell you what it's called. Okay, so there's a third right-hand rule, and it's very, very funny. Okay, so I guess I need to do a little bit more. Okay, so it turns out that we are going to, on your final exam, I'm going to show you a picture, and it has to mean something to you. So, you know, what does it mean? How does it work? So the answer is I need to teach you, right? So the question is, how do I show you the direction of a magnetic field, right? How do I show you? Well, I could show you like this, right? I can show you the B field like this. I can show you the B field like this. I might even try to show you the B field, you know, going in a loop like this, right? But what if the B field is not in the plane of the paper at all, right? What if the B field is coming out or going in, right? So suppose that I'm looking down at the top of the magnet or the top of the Earth, right, or something like that. What would I see? And so what I'm going to tell you is that I won't often do it, but if I draw a picture like this, and I tell you that it indicates the magnetic field, that's really sloppy. Wow, this is so sloppy. Okay, just pretend it's perfectly beautiful. What does this mean if I tell you this, right? So what does it mean when you see a picture like this? What direction is the B field pointing? Well, the idea, some of you have seen this before, is that you're looking at the tip of an arrow and it's coming out at you, right? It's like the tip of an arrow coming out. Right, there you go. I found the camera, okay? So the B field is coming out of the page, okay? And what if it's pointed into the page? Then that one's a little bit easier. I won't even put a circle around it, although sometimes people do, but often they don't, which is probably what I'm gonna do, which means this is probably the more likely way to do it because it's a lot easier. This is the B field. Which direction is it pointed? And these are the tail feathers of an arrow, right? And so you see them at the back, like a fletching. Yes, very good. And so the arrows, this is into the page. And so it turns out that's going to be the two scenarios that I need you to understand, just because it turns out to be more convenient for drawing pictures on an exam. Okay, so are you ready for the third right-hand rule? Okay, well, what is the third right-hand rule about? It actually has a name, and just ignore this writing over here. This is scratch paper. Oh my gosh, I'm running out of paper. I got paper. All right, I got more paper. I have thousands and thousands of sheets of scratch paper. Okay, I'm not kidding. Maybe even more. Okay, so the third right-hand rule, I'm actually going to go back to our assignment again, and I'm going to show you our assignment. Has a link right here, and you want to write this down, the Lorentz Force. Okay, write that down, the Lorentz Force, Lorentz Force. Okay, Wikipedia Lorentz Force. So the Lorentz Force is the electromagnetic force. Now, I'm actually not going to look at the entire part of it. So let's just take a look at this equation. Here's the equation right here. So hopefully you wrote it down already. But we're going to look particularly at the magnetic portion of it. Okay, so this is a vector. The force vector is Q times the electric field vector plus, ooh, what a mess. Okay, Q means the charge, V stands for the velocity, and the B is the magnetic field vector. Okay, so you wrote that down. F equals QE plus QV cross B. Okay, so the X in the middle is called a vector cross product. Okay, it's like multiplication for vectors. Okay, so in fact, that's what I'm going to be teaching you with the third right-hand rule. Okay, so this is our equation. So this first part, you might recognize this. This is the electric field, and we actually already did this. We did this thing already. This is the electric force, right? This is a force from the electric field, from the electric field. Okay, and then this other piece is the force from the magnetic field. Okay, so that's what this is. Okay, so there's two pieces to it. So we're really going to focus on this piece today, right? But this is what it's called, the Lorentz force. The complete Lorentz force includes an electric and magnetic field component. Okay, but how do you do this thing? Okay, so the answer is you have to learn how to multiply vectors. Okay, so we are not going to do all of that. Okay, we're not going to do all of that, but I'm going to teach you anyways, and you're going to be like, why are you doing that? Well, because I am. That's what I'm doing. Okay, because it's cool. That's why. Okay, because it's cool. So another way to write this, and actually I'll write it on the test like this. The magnetic force, that's what I'm trying to show you right here. The magnetic force, or the force from the magnetic field, is just the second part, Q, V, cross, V, like that. That's what it is. So the magnetic force is going to be QV cross B. Okay, so what does it even mean? What's going on? Okay, so in order to teach you this, I need to make sure you remember how to draw in 3 dimensions. Okay, so anybody remember how to do this? Okay, so I'm going to show you a 3-dimensional picture. I know 2 of them are actually just fine. That's not a problem. And the third is going to come out towards us at an angle, right? This is meant to be pointing out towards us, right? Coming out towards us, kind of obliquely, something like that. Okay, so it's like the corner of a cube or something like that. And what I'm going to tell you is the way that I learned it, which is fine. You know, if you learned it a different way, this is going to be the way that I learned it. So I'm going to teach you because it works for me. I want to teach you what works. This is the direction of positive X. This is the direction of positive Y, and this is the direction of positive Z. So X, Y, Z. You guys are probably familiar with that, okay? And then, and now you're ready. Okay, so now I'm ready to teach you. Okay, so the third right-hand rule, I'm going to teach you my version because I like it. I like it. It's so simple, okay? So the third right-hand rule involves the right hand, of course. And you start off by making a little gun, like when you were a kid, maybe. Maybe you didn't do this when you were a kid. By the way, never point guns at people. Okay. But when you were a kid, you might have played pretend gun. I don't know, maybe not. But anyways, I'm trying to figure out. There we go. All right, I can just go back. Okay. So I'm shooting a gun. There's a gun. Okay. And then you stick out your middle finger, right? Not by itself, but with the other fingers involved. Okay. So I'm going to teach you my version of the right hand rule. Okay. And if you notice, it doesn't look like what you guys saw a second ago. Oh, it doesn't at all because I can't find the camera. Okay, there. I can't do it because everything's mirrored. Oh, it's very.
I can see it. It's there.
It's hard. Okay. Okay.
Is
Oh my
the x-axis
God.
supposed to be your index
Oh,
finger?
my brain is hurting.
Yeah, that's what I'm thinking.
All right. Can you see
And
it?
then
Oh my
the
God, it's hurting my brain.
z-axis is your thumb, and then
There we go. Okay.
the
Okay.
y-axis is your middle finger.
Okay. So yes. So this is my X. This is my Y. And this is my Z. I think I finally have it. It's really hard because it's mirror reflected in my video camera. So anyways, but I figured it out finally. Okay. So it turns out this is a kind of a cool rule. So if you ever get confused, by the way, computer programmers, if you are doing any like vector kind of manipulation and you're getting confused, if you just hold your hand up at any orientation, this is correct. Positive X, positive Y, positive Z. These are in the right orientation. And that's kind of important if you're going to do like vector manipulations of graphics or something like that. Okay. So now how does this work? If you go back to the equation, can everybody see that there are 3 vectors? Where are the 3 vectors? Well, there's the F, there's the V, and there's the B. And so what I'm kind of teaching you is a very limited version of what you can do with this, but it's a really cool part of it, okay? And so what's really important is that if V is perpendicular to B, there's a force. But if they're not perpendicular, if V is parallel to B, then there is no force. This is kind of a weird idea. But if these are not perpendicular, see, X is perpendicular to Y. If you tried to move X over here, it wouldn't work, right? That's not Y. I mean, there's Y over here. So I'm kind of mixing things up. But the idea is that F is perpendicular to B, there is a force, right? You get one. But if this is parallel to B, there's no force. Okay, so here's the way it works. It turns out that the V is going to be like the positive X, and the B is going to be like positive Y, and the force is going to be like positive Z. And I'm actually just teaching you how to do a vector cross product in a visual way, right? I'm teaching you a mathematical thing, but just using the directions, okay? So we're not worried about any of the math behind this. It's really beautiful math, it's cool, but way too much time to get there. So we're just doing this kind of conceptual idea, but it's enough for you to figure out what's going to happen. And that I think is the best part of it, okay? So we're about to take our break. I know we need to break, but let me just finish this right now. One more time, let's go back to the visual, okay? So the reason, again, why I like this is when you point your gun, the velocity of the particle is the direction of your gun. It's like firing the gun, right? So your bullet comes out. Well, that's the direction it's moving. The middle finger is the direction of the magnetic field. And in the problems that we're going to be doing, you're going to have to use your paper. Where's my paper? Oh, I could put it on the paper. But the idea is the magnetic field will either point up or down, right? Out of the paper or into the paper. Now, again, you can do any problem you want, but the 2 problems that I am asking you to be prepared to do, and on the homework and for the final, is going to be in or out. Okay, that's the middle finger. And the direction of your thumb is the direction of the force on a positive charge. This rule is for positive charges. Now, some weird people will tell you to learn the left-hand rule for negative charges, and I don't do that. I don't care about it. All I do is, if it's a negative charge, my last step, because it's negative, is to take the negative of the answer. Because Q is negative, you just flip it over, right? And so for me, why bother having 2 different formulas when all I have to do is flip the direction over at the end? So I pretend that the charge is positive no matter what. And then if it's a negative charge, I just flip my answer over because that's what negative charges will be. Okay, everybody clear? Okay, so let's take a look at a real life problem. Okay, and then we will take a break. Okay, so here we go. Here we go. Are you ready? So I have a region where there is a magnetic field. What direction is the magnetic field apparently?
Down.
Is down, right? And now I'm going to shoot a particle in. Actually, in fact, let's shoot two particles in. Let's shoot a positive particle in with a velocity vector like this, and a negative particle in with a velocity vector like this, and a charge with zero charge, a particle with zero charge with a velocity vector in, same velocity. Okay, everybody understand? Okay, by the way, if there's zero charge, what's going to happen? What's 0 times anything? The answer is what? It goes straight through. It's undeflected. Undeflected. This is kind of cool. So actually, if you're a scientist and you want to determine if a particle has charge or not, you're going to find out this is an amazingly powerful way to do this. This is an analyzer. It lets you analyze the charge, right? Figure it out. Okay, now let's use the right-hand rule on the positive charge first. So start off by pointing your gun the direction of the velocity. Okay, so the velocity vector is this way, pointed this way. And then you have to rotate your middle finger so that it's pointing down into the page. And which direction is the force? And the answer is towards the top, right? So as soon as it enters, what's going to happen? It's going to feel the force pushing up like this. The magnetic force is going to push up like this. Ooh, I forgot something. Ooh, I forgot something. Oops, I forgot something. Here I am, a charged particle with a velocity, QV, right? What happens if you push in the same direction as the velocity? What happens? If the force is in the same direction, what happens? Anybody? You speed up, right? Well, it's always accelerate, right? You speed up though. What happens if the force is in the backwards direction? Slow down. But what happens if the force is perpendicular to the direction of the velocity? Do you speed up or slow down? You turn is correct. That's right. So don't fall for my trick. You don't speed up. You don't slow down, which means that all you could do is turn. So this is one of the questions I'll ask you on the, oh, I wrote the quiz, never mind, whatever. One of the questions I'll ask you on the homework is, how does it turn, right? And so the answer is, if you watch it, you will see a positive charge move on a circular path. And there's actually a radius for that path. And that's actually one thing we're going to talk about when you come back from the break, okay? So it's going to turn, right? It's not speeding up and it's not slowing down. Acceleration means the change in velocity. Yes, deceleration is a word for non-physicists, but in physics, we talk about acceleration, change in velocity, the rate at which velocity is changing. So you either speed up, you slow down, or you turn, or you do all of it, right? Or, well, you can't do all of it. You could speed up and turn, slow down and turn, just turn, speed up, just slow down, right? Those are all considered to be acceleration. Okay, let's do the negative charge. Okay, so I do the same. Actually, I should do the same thing, right? The velocity is the same direction. The magnetic field's the same direction. So the answer is up, except it's a negative charge. So at the last moment, what do? Flip it over. So now my thumb is pointed towards the bottom of the page. And in fact, the force is going to be down, which means it's going to curve like this. And there's going to be some radius of curvature. All right, everybody good? Okay, let's take a 10-minute break. 10 minutes, or how long do I give you guys? 10 minutes? 15? I don't want to kill you. 15? 10, 15? How much do you need? How many of you won't take any break?
15 would be nice.
Okay, 15. All right, 15-minute break. Go to the bathroom, get something to eat. And yeah, because we do want to finish on time though, because I have to get the speaker going for at the 1 p.m. Okay, thank you guys. We'll be back at 15 minutes. And that will be 11:39. Okay, back at 11:39. Oh, I can do this here. Oops. Okay, I'm back. You guys ready to go? Okay, 11:39. It's 40 actually. I'm late.
Ready.
All right, let's do it. Let's do it. Okay, so just to kind of get ready to do real problems, right? Let's go back to this equation. This is the magnetic force, and we figured out how to find the direction. So let me keep going. So equals Q. Oh, that's no direction. V cross B. Okay. So if I understand that the direction I get from the direction from the right-hand rule, number 3, right? Number 3. Then I can talk about how big it is, right? What is the magnitude of the force? Okay, what's the magnitude of the force? What's the magnitude? And so the answer is it's just Q times V times B. If V is perpendicular to B, right? Right? And it's 0 if V is parallel to B. Right? There's no force. So this thing only works when the V is perpendicular to B. Now, some of you might say, well, what if it's not quite perpendicular and it's not quite? Well, okay, we can do that. But let's leave that for, kind of for the future. But I'll just let you know, if you want to know the definition of V cross B, what's the magnitude? The magnitude, it's V, B, sine of the angle between them, right? Where that's the angle between them. We're not going to do that. We're gonna leave that. Okay, that's what it is. Okay, so if they're not quite perpendicular, there is actually a force, but what it is only the part of the velocity that's perpendicular is going to count. So maybe, can I show you that? I can show you that. Let me just show you that. So let's say that you have a B here and a V kind of like that, right? There's V. V is like that. What you do is you say to yourself, hey, this velocity has 2 parts, right? It's got a part that's perpendicular to the magnetic field and another part that is parallel to the magnetic field. I might call that V perpendicular and this V parallel. And so which part of this is going to be, did I do this wrong? Oh no, the angle between them. Okay, oops. That's why I use this angle. Okay, so I messed up a little bit. I messed up a little bit because I wanted to use this angle, but that's the wrong angle. Let me just redraw it. Sorry about that. 1 second. So because I defined it this way, I need to actually put V here. Here's my angle theta. And then think about V like this, one piece going up and one piece going over like this. Okay, so this will be V parallel and this will be V perpendicular. That makes sense? Okay, now this picture works. And so the part of V perpendicular right here is just going to be V sine of theta. So that's where it comes from. It's just the perpendicular part that gives you any force. Okay, that I don't care about that. I'm just going to stick with this. Okay, so what are the units of force? We know what they are. They're newtons, right? That's a newton. What is the unit of charge? The coulomb. What's the unit of velocity? Meters per second. And so the last one is, what about the magnetic field? What's the units for magnetic field? Oh, why am I putting, I meant to put brackets. I don't know what I'm doing. Sorry about that, guys. These are brackets, not absolute value, units of. That's why, because I was just using absolute value symbol. I meant to put units. Sorry about that. Okay, what are the units of B? Does anybody know?
Would it be a combination of all 3?
One more time.
Would it be a combination of all 3?
It could be, but we're actually going to, yeah, it is. Actually, you could derive it. In fact, that's a great answer. That was a wonderful answer. I like that. But we're going to go ahead and define it. And it's called, you're going to like the name, Tesla. Capital T. No, Tom, that's another unit. Yes, we can get to Gauss if you want to, but this is the unit that we're going to be using. This is the SI unit of magnetic field. So Tesla, actually interesting, right? The name of the car company is also the unit of magnetic field. It is pretty large, by the way. A Tesla of magnetic field is very profound. And so there is another unit Tom put in the chat there called the Gauss. And that is, what's the relationship? 10 to the 4th. Gauss is 1 Tesla, something like that. I should know that. I just, who knows the relationship? Tesla, Gauss. 10 to the 4th, I think. 10 to the 4th. Yeah, that's it. Okay. So Tesla, if you want to use Gauss, it's 10 to the 4th. Okay. 1 Tesla is 10 to the 4th Gauss. This is another unit that people have used. And the interesting thing is the reason why maybe is kind of important, because the magnetic field of the Earth, oh yeah, the magnetic field of the Earth, this is actually why we use it, I think, is about 1 Gauss, right? I want to say that mag field. I'm looking it up just to make sure I'm not stupid here. Okay, Earth magnetic field, and I'm not stupid, I just haven't seen it in a while. What is it? It is 0.25 to 0.65 Gauss. Yeah, it's like a Gauss, right? I guess not quite a Gauss. 0.25 to 0.65. Okay, all right. So it's kind of closer to, yeah, half a Gauss. Okay, magnetic field of the Earth. Tom says about 0.5. Yeah, that's pretty good. It says 0.2 to 0.6. It's about a half a Gauss, 0.5 Gauss. So the Gauss is going to be kind of the weaker magnetic field, something like the Earth. But in terms of in physics, it turns out, and astrophysics, of course, the Tesla is going to be a more useful unit to use. Okay, so anyways, all of that, right? What do we want to do? We want to talk about the force. So I want to talk about what is the force acting on a charge Q as it goes flying through a magnetic field. So I'm going to put this magnetic field, right? And I want to figure out what's the strength of that force, right? How strong is the force? I'm going to start off and I'm going to give you the field strength. So let's say that it's, let's make it, I don't know, how big? It's pretty big. Actually, I'm kind of curious. Oh no, this is too big. Let's put like 0.5 Tesla. Okay, that's pretty powerful, but 0.5 Tesla. And what does the X mean? These are the feathers of the arrow. It's pointed into the page, right? Let's make it a positive charge. Positive charge. Just make it a proton. Should we make it a proton? Sure, why not? Let's make it a proton. Okay. So that means we know the mass as well, right? 1.67, 10 to the minus 27 kg. And we know the charge of a proton, positive 1.602, 10 to the minus 19 coulomb, okay? So what I want to do is I want to use this equation to figure out the acceleration that a proton will feel because of this force, right? So the force is going to be Q times B in the magnitude. But because of Newton's law, a force causes a mass to accelerate. So let's do a problem where we see how much force is on a proton as it flies into a region with a field of 0.5 Tesla. And I have to give you a speed, right? I'm going to give you a speed. So we want to suggest a speed. Don't make it too relativistic. Give me a speed, anything you want. No, C, you're a joker. C. Okay, how about, anybody want to give me a number? Anything? 0.2 C. Okay, well, that's going to be relativistic. All right, you want to do it? Actually, in fact, I'm going to have you guys go, we're going to go relativistic. Yeah, let's start off with something not so fast. Okay, so let's just give it like, let's make it 100 meters per second. That's not very fast. That's pretty slow, actually. Whatever, just giving you a number. It doesn't matter. I just want to give you some kind of number. Okay. All right, so start off. what is the force going to be? So it's all you really have to do is put in these numbers. And I've told you that when you put this together, a Coulomb times a meter per second times a Tesla is going to be a Newton. Okay, so this is if you use the prescribed units that I told you, then you're going to be able to get the right units coming out. So 1.6 times 10 to the minus 19 coulombs, 100, make it exact, 100 meters per second, and then 0.5 Tesla. Okay, so half of that, but whatever. Okay, it's going to be a pretty small force. Okay, so let's see. We got 1.602 negative 19 times 100 times 0.5. Okay, you guys got a number? 8.01. 8.01 times 10 to the minus 18, right? 10 to the minus newtons. Okay, so I got my force. Now, how about the acceleration? Well, so now we've got the force and we know the mass. How do we find the acceleration? Acceleration is the force divided by the mass. So you just go 8.01 times 10 to the minus 18th divided by 1.67 times 10 to the minus 27. Okay, and you'll see, wow, it's actually a really big number actually. But again, the mass of the proton is very tiny. So we expect, even though the velocity is not very fast, we're still going to get a large effect from this. So divided by 1.67 e negative 27, and I get, whoa, it's big. Okay, so I get 4.80 times 10 to the 369, 10 to the 9th meters per second squared. Okay. Okay, does everybody agree with what I did? You got it? Okay. All right, so the proton experiences actually a pretty incredible acceleration. And so what's kind of fun is to understand that that happens, right? As soon as a charge enters a region with a magnetic field, it can't go straight anymore. It can't go straight. Which way is it deflected? We already did this problem, but you use the right-hand rule, right? Your arrow going like that, rotate like this, and it's going to curve up, right? It's going to curve up. As soon as it enters the field, it's going to curve up. So we know, in fact, that if you made the field region big enough, that the charge would actually move on a big circle, right? It would actually be on a big circle. So let's just try that for a second. Imagine that I make a really big region, lots and lots of space. Lots and lots and lots of space. And I shoot my particle in, or maybe I turn off the field, right? And I turn the field on right when the proton is in the middle of this part of the field, right? And so what's going to happen when I do that, right? The field turns on, and now the particle can't go straight anymore. It's going to move on this giant circle, actually. So let's draw the circle, right? There's a circle right here. And the circle has a radius, right? The circle has a radius. And so what I've just shown you is that the magnetic field can be the reason that the object is making a circular orbit. So you might remember that we've talked about circular motion before, right? And we know that, in fact, in order to move on a circle, you need a centripetal force, okay? If this was a satellite orbiting a planet, it's the force of gravity that's making this happen. But in this case, it's going to be the magnetic force making it happen, right? The force that's going to be pushing towards the middle is the magnetic force. So let's remember what that is. What's the centripetal force? Well, it's the mass of the object, right? The mass of the object times the speed of the object squared divided by r. That's the equation. Okay, centripetal force. This is the force you need to move on a circle. If you're moving on a circle, there's a force making you move on that circle. That's what it is. And you might remember that this is the mass times the centripetal acceleration. V squared divided by R is the centripetal acceleration. Okay. So what I want you to understand is for this proton, right, the circle is going to be pretty big probably. We're going to see right now how big it is. I don't know, actually, I'm not sure how big it is. In fact, at 100 meters per second, I don't know what it's going to be, but let's figure it out. Okay, so the proton is going to be moving in a circle because there is this force, but this is not the force. This is the force you need to move on the circle. The force that is being exerted on it is going to be exactly what you need to move in a circle. So this is actually a relationship. The proton moving on a circle must be that the magnetic force that it's feeling is just the right amount to move on this circle here. Okay, so you write that equation down, and now we're going to solve it. And we're going to come up with this beautiful new equation that kind of will be a shortcut to solving some of the problems that you'll have to solve for the homework. Okay, so one more time, the magnetic force that the magnetic field is pushing on the proton is going to cause it to turn and be exactly the amount of force needed to maintain a circular path. Okay, so now we're going to put in what we know. What's the magnetic force? Well, it's Q times V times B. Now you'll notice that in my picture is the velocity perpendicular to the magnetic field. And the answer is yes, always, right? The velocity anywhere in this piece of paper is perpendicular to a vector which is pointed straight down. So that's great, perfect, because that turns out to be nice, because then we know that this is exactly right. And what is it equal to? mv squared divided by r. Okay, so presumably I know the speed, and I know the v, and I know the q, and I know the mass. What do I not know? I don't know the r. So go ahead and solve for r, right? I'll give you a moment to do that. And it just takes a moment, right? And you get an equation. There's an equation. What is the radius of the circle? How big a circle will it be?
The mass times velocity squared divided by the charge, or the force.
Okay, so you did r equals mv squared divided by qvb. That's correct. One of the v's can cancel though, right? So we can do that. And it's just the mass times the velocity divided by q times b. There it is. It's the radius. So let's take our earlier problem, the problem that we just did, right? Suppose that the proton is, we shoot it into this region where there's no magnetic field, and then we turn the field on. And now the protons will start circling around. And okay, we can get that. All right. So what's the radius of that circle? Well, so I've got to put in the numbers here. 1.67 times 10 to the minus 27 kilograms. Okay. The speed 100 meters per second. That's pretty small. In fact, many of the problems I think we're going to need to go relativistic, but for today it's fine. Okay. The charge 1.602 times 10 to the minus 19th coulombs, and the magnetic field 0.5 Tesla. Okay, and so let's get an answer, right? You guys get. Okay, so 1.67, they get an answer. Why don't you type your answer in, and that way I can check against my answer. Times 10 to the, yeah, I got the same answer as Lonnie. Tom, I don't know. Did you mean -7, Tom, or? It's 1.67. Oh, your head didn't work. Yeah, that's correct. Your head didn't work. Okay, here we go. So 2.08 times 10 to the minus 6 meters. Okay, well, that's pretty tiny. That is tiny. That's 2 micrometers. That is a tiny little radius. Okay, that is tiny. Actually, that's smaller than a little dot, right? So actually, what's kind of fun is if you wanted to, if the protons weren't going very fast, you could trap them in a magnetic field because they would move around in little circles, right? They wouldn't get away from you. You could trap them, right? Okay, so that's kind of funny. Oh, you want me to show you how the units canceled? Oh man, okay, now I'm in trouble. Oh my gosh, I'm in trouble. Okay, let's see. Okay, let's go back to this. We know that a Coulomb times a meteor per second times a Tesla equals a Newton. How about that? Okay, so because this is the force, right? So this must be true. Okay, can I go there? And then you're okay. So a Tesla is a Newton divided by a Coulomb divided by a meter per second. How about like that? Okay, so now you can go over here, you can say kilogram meter per second Coulomb times a Newton per Coulomb meter per second. The Coulomb cancels. So you get kilogram meter squared per second squared per Newton. Okay, but a Newton is the same as a kilogram meter per second squared, mass times acceleration. And so you get, cancel the kg, cancel one of the m's, both of the s's, and you get meters. Is that okay? Okay, great. It's beautiful. I love that. That's awesome. Okay, so this is pretty tiny. Let's just for fun, let's suppose I ask you the question, right? What V is needed for a radius of, I don't know, about a meter? Let's make it exactly a meter just to make it a nice whole number, right? So now we're gonna try to work in reverse here. We shoot this proton into a region with a magnetic field, but I'm telling you, I want the radius to be 1 meter. I want it to be a nice big, human-sized radius. And I don't know how I'm going to do that. That's a bigger apparatus, but I want to do it for whatever reason. Now you're going to invert this and figure out the speed. So how will you do that? Well, you're going to start with the same equation, right? You start with this equation that we figured out, which is mv divided by q times b. And you're gonna figure it out. Okay, now we know radius, we know the mass, we know the q, we know the b. How do we figure out the speed that we need to get the right radius? Okay, so we want to invert this equation. Okay. All right, so just rewriting the equation, V must be equal to Q times B times R divided by M. Bam, there you go. That's right. QBR, RQB, whatever, divided by M. Okay, let's do it. Let's find the speed that you need to make a 1 meter radius, right? So we got V equals Q times B times R divided by M. We got 1.602 times 10 to the minus 19 coulombs. 0.5 Tesla field. Okay, the radius we want is nice and simple, 1 meter, and the mass is 1.67 10 to the minus 27. Okay, that would be kg. Okay, now these numbers are similar, so you could just, if you want an order of magnitude, just cross it off, but the order of magnitude is different, so you get 10 to the positive 8. So the answer is about 5 times 10 to the positive 7, roughly, right? So then we can do the actual answer. Okay. Can I get an answer?
4.79.
Yeah, we might round it up to 4.8.
Yeah, to the 7 or to the 8. 1,
the what?
2, 3, 4, 5, 6 to the 7.
10 to the 7. Okay. So now I'm going to ask you guys, is that relativistic or not?
Maybe.
Maybe. Is it relativistic or not? Okay. Maybe. Okay.
Probably not. I feel like it has to be in the 10 to the 8 to be relativistic.
Well, what's 0.1c? 0.1 times 3 times 10 to the 8th. 3 times 10 to the 7th. 0.2c. Are we
Okay,
getting
so-
close to relativistic maybe?
Yeah, the gamma would be. Wait, no, the gamma
Oh,
would.
something- Yeah, we didn't do anything with gamma. There's no gamma here, right? There's no gamma involved here. This is, well, there's a problem. Actually, why would relativity play a part? Where does relativity play a part in this? Do you see any? Is there a place for relativity? V is speed. Q is charge. Magnetic field is B. R, M. Is there any place for relativity here? The charge is the
No.
charge. The field is the field. Yes. Well, my question is, which aspect of this will change? This is not kinetic energy, for example, right? What happens to, I mean, I guess maybe there's relativistic length contraction or something. But it turns out that the number one place, yeah, actually that turns out to not be there. Yeah, it turns out, I'm not sure that that's a problem either. It turns out this is the biggest problem, right? If you remember, the mass is gamma times m0, the rest mass. So the mass becomes more the faster you go. So yes, if we go too fast, then this mass changes and we need to put a gamma in there, I guess. Yeah. Okay, so we'll have to deal with that. We'll think about it a little bit more. Okay. But anyways, it gives you a little bit of an idea. Now, actually, so I did all of this. I went off in a little bit of a different direction than I was originally planning to, because I actually wanted to tell you something kind of amazing. I'm just going to tell you, write it in words. A charged, maybe I should blow your minds first. You want me to blow your minds first?
Yes.
Okay, let me just do something for a second. Okay, so if I see a charge just standing still, Q, remember how there's an electric field? They have positive Q, right? There's an electric field, right? So I'm going to write something down for you. In the frame of reference of the particle is not moving. So there is only an electric field. Okay. So now I want you to go back to imagine that you're not writing with the electron, with the charged particle. You want to watch this charged particle go flying up. I see it. It's got a velocity. It's got a positive Q like that, and it's flying up. Is there an electric field still? And the answer is there's still a charge. So of course, there's still an electric field. But now I see it moving. And I want you to blow your minds just a little bit. I want you to imagine that I've drawn an imaginary wire here. And now when I see charges going up, I don't think about them as charges going up. What do I call that? Electric current. Right? So when I see the charge moving, what happens? I see current. And we learned the first right-hand rule, right? If you have a velocity or a direction for the charges like this, the magnetic field wraps around in circles. There's a magnetic field. We see the charge moving. It has E and B. This B comes from the relative motion. What if you don't want there to be a magnetic field? There's a trick in physics. If you don't want to deal with magnetic fields, what's the magic trick? Change your point of view to be in the frame of reference of the particle. There's no more magnetic field. It's gone. Okay, that's supposed to blow your mind. The magnetic field is something that occurs when you can see the charge moving, and it's not there in another frame of reference. So in some sense, it's what you see because of your perspective, right? So we've already learned that time is relative, right? Time is relative. This is kind of like a similar kind of concept, the motion of objects or what we see, electric and magnetic fields are not always the same, right? So we perceive a magnetic field when we see the charge moving, but we don't in this case. Anyway, okay, that's supposed to blow your mind. I don't know if it worked. Okay. Well, it blows my mind. It makes me feel a little bit weak in the knees. It's a good feeling. I like it. All right, but now I'm going to tell you the important words. Okay, I'm just going to say the words out loud, okay? A charged particle that accelerates emits light.
And that's why ion propulsion emits that light blue light?
Well, no.
No?
Maybe, but I don't know. Probably not. Yeah, Cherenkov is one version. Actually, it's really different. It's really different. Well, Cherenkov radiation is good. That's fine. But actually, this is yeah, synchrotron is kind of what I wanted to get to. But anyways, it doesn't matter actually, and it doesn't matter how much acceleration. There's going to be light, right, coming out of an electromagnetic wave, EM wave, right?
This is related to like the auroras in the northern lights.
Well, it's connected, definitely. So let's start off with something super simple that is also kind of neat. And I have it in my links here for you guys. Actually, it's not simple. Sorry, let's start up with, let's do something. We're just jumping right in. Oh my gosh. Okay, and actually, you know what's so funny? I've never done this with any students before. You are absolutely my first. And I hope you feel special because I felt like you guys might appreciate this. So we're not going to derive it. We're not going to really try too hard, but I'm going to ask you to believe me that an accelerating charged particle will emit light. Okay, so, and we're going to click on this Larmor formula. Okay, now I haven't done this since I was a grad student, so I am not super, you know, I'm not going to be able to do really complicated problems with you, but
you can capture that light, by the way.
Huh?
You can capture so a little out of each side of the visible light spectrum. You can capture with a regular DSLR.
Oh, I've heard that. Yeah. You mean you can catch like infrared and ultraviolet?
Right. So if you have, like, for example, I have an old full frame camera that I'm looking to convert, and I was looking to do an infrared conversion, but then I thought, well, why don't I just do a full spectrum conversion on it? And essentially what they do is they remove the aliasing filter and the IR filter and put a clear filter on it, and it captures. So essentially, you can put something on your lens to make it capture specific wavelengths if you wanted to, but you can use it as a normal camera, but it'll capture everything.
That's cool. You guys understand what
UV
he's
to
saying?
IR.
He's saying that the standard cameras come with filters to block the infrared and ultraviolet light. I guess somehow they make the picture not as sharp or something, or I don't know why they do that.
Well, it's done on purpose to be able to a little bit more pleasing to the eye, but
okay.
more and more we're looking at sharper and sharper images because that's what our technology can do. But there are services that remove those filters and allow the camera to have a lot more flexibility, and they're especially useful for astrophotography because of the ability to absorb the UV and infrared lights. You're able to see things that you would normally not see in the sky at night.
Oh, that's awesome. Okay, cool. Well, you're gonna have to share that with us when you start doing that. That sounds wonderful. Okay, so take a look at this formula. Here it is, the Larmor formula, and just write it down just for fun. I mean, that's all this class is supposed to be. It's supposed to be fun, right? But the P stands for power, right? The power, the total power, which means in any possible frequency, by the way. So this is not giving us the exact color of the light. There's a little bit more to this formula, but I will describe a little bit for you. But the total power is Q, the charge, squared, times A squared, the acceleration, squared, divided by 6 pi. Epsilon 0 is a constant, and then C to the third power. Okay, so there's an equation. And anyways, this is the equation. All right, we're not going to worry too much about in either system, the power rated by a single electron can be observed. We're not going to do that. Okay, so anyways, I have an equation here. That's cute. Let's just talk about it for a moment. Okay, all right. So yeah, what are you going to use this for, Christian? For astronomy, right? Tom says don't. Never mind. Okay. All right. So Q, A, and epsilon 0 is a constant, right? So permittivity of free space, the constant. And who knows the number? 8.85. I don't know. I can't remember the number. 8.8 permittivity. Epsilon 0 is called epsilon 0. Epsilon naught. Vacuum permittivity. Okay, I'll just show you right here. This constant has a value that we can look up, and I just looked it up right here. So it's the vacuum permittivity is 8.85 times, you can put 8.854 if you want, 854 times 10 to the minus 12th. And then what? Okay. Oh gosh, I don't like the units though.
Is that, what are those units? Force?
That's a farad.
Farad.
That's a unit of capacitance. Farad per meter. Farad. Okay. Okay, I need some help with that one. Let's see. Here. Oh, that's what I should have just told you. Hang on a second. This is actually, do you see the 1/4 pi? Pi epsilon 0?
Yeah.
That's K. 8.99 times 10 to the 9th.
Oh, and K is Coulomb constant.
Yes, that's right. Newton meter squared per Coulomb squared. Okay, that's easier. That's actually what we should do. Let's just do that. Okay, so it turns out that this is true, right? This is a constant which has farads per meter, but let's not worry about it. This value is exactly the K Coulomb constant that we had before. And so you can see we're just missing we could throw a 4 in if you want and multiply by 4 here. And then this piece, right, 1 over this piece changes it into, let's see, put the 4 here, put the 4 here. Okay, so 4 q squared a squared k over 3 c cubed. Okay, so now I've got the Coulomb constant. Oh no, I messed up. Sorry, 6. I could have reduced it. That's right. 2. Oh man. 2, 3. Okay, one more time. 2 q squared a squared k. That's the Coulomb constant over 3c cubed. Okay. So, but this is the total power, right? So I don't know that we're going to be using this too much. I just wanted you to be aware of it. And this says the total amount of energy per second that's being radiated by a charged particle. Okay, so I have 2 more little things that I want to do with you. And one of them is just very quick and conceptual. And the other one is going to take a little bit of work. So that's probably going to use up the rest of our time. But let's go back to our page one more time. And I'm going to show you this. This is really fun. Okay, so you go to radio waves and electromagnetic fields. And again, this is a Java app. And so I'm going to go ahead and now switch to that Java app and show you what it looks like. Okay, so here we go, Java app. Okay. So this is over here, KPHET, it's a little joke, FM 98.7. Does anybody know what that means? We've talked about that before. What does that mean? FM 98.7. Anybody remember? That's the frequency. It's 98.7 megahertz, if you remember. That's the frequency. Anyways, whatever. Okay, here is an electron inside of a pole. This is also called an antenna. All right. And so what do you do with an antenna? You push on it with electricity. And that's actually what the radio station is doing. They're pushing on the electrons inside of the antenna, and they're making them move, accelerate, right? And did you see what happened? What just happened? Right? Some radio waves went away from the electron because of the way I did that, right? So there's this pulse as I accelerate that, right? And what they do with the radio transmitter is they don't just do a single pulse, they oscillate, right? They make the electrons go back and forth, up and down inside of the antenna. And so you get these waves coming out of the antenna, and at your home or wherever you happen to be, when you want to listen to the radio, you need an antenna. And the antenna works because it has electrons inside of it. And the electrons are moved by the forces that are exerted by the waves, right? Actually, you want to be very careful. What part of the wave are we seeing right here? This is the electric field, okay? So remember, it's an electromagnetic field, but only the electric field can make it move like this. The magnetic field cannot, okay? Magnetic field can make it move in circles, but there's no way the electron can move in circles here. So in fact, the magnetic field doesn't do anything. It's just the electric field, okay? So that's just a simple demo for you to try to show you the idea. Capture, send, radio, AM, FM. What's PM, Tom? I don't know PM. PM. Unless it's, oh, phase modulation. Okay, cool. Okay, so different ways of creating waves, but what you're doing is you're accelerating the electrons, and then in response, the electrons are creating a wave. Okay, now the final little topic that we want to get to, and this is really useful, turns out to be probably amazing. I used it in my dissertation, in fact, is our final idea is the concept of synchrotrons. Okay, so synchrotron, so you need to know what it is. What is a synchrotron? What is a synchrotron? How does it work? And why is it special? Like what's the kind of a cool, neat thing about this, okay? So the topic is synchrotrons, okay, our final topic. We only have a few more minutes. And these are a big deal. These are particle accelerators. That's actually what they're doing. But they are special because they are rings. Okay, so you might write down that it's a ring. It's a ring. And one of them is a really famous one called the Large Hadron Collider, which we may have talked about it. Oh yeah, I think we probably did. Yeah, I think we did. Accelerates beams of protons to an energy of 6.5 tera electron volts. So the reason why they're useful, let's click to applications, is wow, this is so not useful. Okay, so let's go back up. Here we go. Okay, so there's more than one reason, but the biggest thing, actually, this is the one. This is not the one I used. This is the one I used. Brookhaven National Lab. I actually did experiments there at the synchrotron, and the reason I did, just so you guys understand, is that the light that I was using was X-ray light. It was a source of X-ray, and the frequency of the X-rays was very how should I put it? Very clean, very monochromatic. Oh, that's not the right word. It was almost the same frequency, not perfect, because there's always a little bit of spread in the frequency that you're using, always, but the spread was very small. And so it allows you to use a very precise color. And in my case, it was a synchrotron light source. Okay, so synchrotrons has a wide range of applications. Synchrotron light, maybe that's what we should just look at. Let's look at that. Here we go. Synchrotron radiation, what is it? Magnetobremsstrahlung. Oh, I did not know that. What the heck? How about that? All right. Magnetobremsstrahlung. I didn't know that's what it was called. Wow. Okay. But anyways, the way it works is you make the charged particles move in a circle. They're accelerating because they have a centripetal acceleration. Okay, so let's just go ahead. All right. This looks kind of cool, actually. Properties. They have broad spectrum from microwaves to X-ray, high flux, lots of energy. Polarization, that's actually a really interesting thing too. Okay, I don't think I have enough time. Okay, and then is blah, blah, blah. Okay, synchrotron radiation from accelerators. Synchrotron radiation may occur in accelerators either as a nuisance, causing undesired energy loss, or deliberately to produce a radiation source. And that's actually what I think is kind of neat. So it turns out that the proton bunches produce radiation at increasing amplitude and frequencies as they accelerate with respect to the vacuum field, propagating photoelectrons. Okay, synchrotron radiation in astronomy, and here's where we can actually look for this in space and then try to figure out what we can from that. So let's see. Okay, in particular, guess what? That Crab Nebula that I was showing you, it actually shows synchrotron radiation coming from it, but not just from the core. It turns out from other parts as well. Okay, so blah, 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 blah. Oh man, this is too complicated, isn't it? Oh my gosh, that's too complicated. Oh, way too complicated. Oh, too complicated. I don't think we can do this. It's too much. Okay, so the source of it, I think it's too much, huh? It's too complicated. I thought there was. What was that?
There was some integration there. Yeah, I mean.
Yeah, that's too much. Okay, why do you keep in the sync? Brox. Okay, sorry. Bremsstrahlung. Bremsstrahlung are breaks. Strahl is this. What? Do you keep it in the sync? Oh, you're funny. Oh my God, I just figured that out. Okay. Tom is telling jokes in the chat channel if you want to read those. Okay, so anyways, so this radiation that comes out is a result of, okay, let me just talk to you guys. So the radiation that comes out is a result of the fact that it's accelerating. So I was hoping we could get a frequency, and I want to tell you it's very simple. Actually, I probably could have showed you, actually, I can't show you that. The frequency, okay, I'll tell you this. Okay, so if you make an electron oscillate back and forth like this, the frequency that you make it oscillate turns out to be exactly the frequency of the wave that will come out of it. Did you hear me? Right? So the frequency of oscillation of an electron. Well, so how would that work with a synchrotron? So in fact, the synchrotron, the particles are moving in a circle. And because they're moving in a circle, they're going to go past a given point a certain number of times per second. Is that how you get the frequency? Actually, I kind of want to say that's it. Except that can't be quite right, is it? It seems too easy. Seems too easy. It's angular dependence. It's not that simple. Okay, so I know I can't just do that. It's not right. It's not right because I won't even tell you. But in this ring, you got different frequencies coming at different angles. And actually people would set up their experiments at different angles away from the central beam. So that's not right. Not right. I can't just say it. So it's not so simple. Anyways, I thought it would be a little bit easier, but it's not that easy. Okay, so the key idea though is there's these devices called synchrotrons. And in fact, in the early days, a synchrotron, a cyclotron, actually is a slightly different word. Maybe we should see if we could find that.
Well, I've heard of cyclotron.
Have you heard of that one before?
Oh yeah, Ricardo tells me about it all the time.
Oh, cyclotron?
Yeah, cyclotron.
I used to use one.
Who you used one? Who used one?
Yeah. So we had one to generate what was it called? It's for the lithography process. We called it a matrix asher, and you would generate this high energy plasma that would basically ash off, burn off a layer of stuff on a silicon wafer.
So the particles that you come shooting out are going to burn off or etch. Yeah, you're gonna kind of eat away at something on your wafer. Okay.
Right, and it generates a high energy plasma inside of a chamber, inside of a vacuum chamber, and then it's used in creating literally everything in microelectronics.
Wow. Okay, I didn't know that. Okay, so let me tell you a little bit of the history, the part that I know. These things, they're a little complicated, right? But they use a magnetic field, and you can see a particle spiraling around. And so something's happening. You're actually speeding them up, speeding the particles up, so that the radius is getting bigger and bigger and bigger. But the reason I was thinking about them is actually during World War II. The reason why they were used, or something like this, is for isotope separation. So let me just see if I can find that. Isotope. Who knows what an isotope is?
It's a particle that's decaying over. It has a certain decay rate.
Yeah, same element, but different numbers of neutrons, which means different numbers, different mass. Okay.
Yeah.
So the original technique for taking uranium, and by the way, is all uranium used inside of the original nuclear bombs?
No.
The answer is no, right? Or plutonium here, or whatever. It's not all of it. It turns out that only some of it is useful. So you want to be able to separate the isotopes. Here is a diagram. And what they've done right here is they're going to take a charged particle. They're going to shoot it out here, right? And what's out here? Okay, so these are going to be ions of an element, which means that they have been ionized. So what does that mean? They have taken they've taken some of their electrons away. So are they positive or negative?
Positive.
They're positively charged. They come shooting out of here. Get out your right hand right now, please. Get out your right hand. Okay. Your finger should be pointed straight up, right? Now, how do you make your thumb point to the right? Which direction does your middle finger have to point?
To the left.
No, wrong answer. Got to be either into the page or out of the page. That's the one.
Out of the page.
That's the answer. Okay. So in this region, the magnetic field is pointing out of the page. And so what happens? The positive particles curve on circular arcs. And there's two different isotopes. One is U-238 and the other is U-235. What's the difference? Just 3, right? 3 neutrons, right? 3 more neutrons, 3 less neutrons, one or the other, right? And so which one has more mass? Well, this one. So which one has a bigger arc? Which one has a bigger radius? The larger
238.
mass. If you go back to the equation for radius, where does the mass show up? If you go back to the equation for radius that we calculated, it's in the numerator, right? So larger mass, larger radius. You can kind of think about it because more mass means more inertia, the harder it is to turn. And so in this particular situation, we have an apparatus, and what they wanted to do is separate the stuff that they didn't want from the stuff that they wanted, right? And so they shot ions of uranium, and then automatically, the more massive ions traveling on the bigger circle were left out, and only the smaller mass ions would make it into the collector. And these were then collected to be able to eventually make a bomb. Now, you had to do this multiple times, by the way. You would take this collector and take it back here and heat it and do it again. You do it a number of times until it was refined more and more and more. It's called the colutron. And this is actually a very simple, it's not even a full cyclotron, but it's part of a cyclotron. Okay, so yes, finger points towards the heavier one. Okay, good, all right. So I'm actually finished now. That's about it. And so what I need to do is kind of make up some problems for you. I'm gonna have a number of problems. I did make up a couple of questions to put for a quiz for your participation. So please do them. They're really incredibly difficult. And so I'm sure most of you are going to get really low scores, but give it a shot. Give it a shot. You know, it's worth a try, and maybe you can do okay. And then what I'll do is I will post practice questions for you to solve for next week. I didn't get to kind of a fun thing would be to try to predict, but actually maybe I can. I don't know if I could do it. We didn't get to the frequency. It turns out I think it might be too hard. I thought maybe we could figure it out, but I think it might be too hard to figure out the exact frequency of the emission. Although maybe we can try to use what I mentioned, that if you say that something is moving in a circle, what about you calculate the number of times per second it goes around and just like calculate that frequency, and it may be loosely connected. I don't know if it is actually. But anyways, okay, so that's about it for today. If you guys are interested, there's a great talk coming up. I'm about to go get ready for that speaker, and it'll be streaming live. It'll be on YouTube because we're hoping we have a couple hundred people show up, or at least 100. And it would be great if you guys would come. And if you need an outside activity, it'd take you an hour. He's a really funny guy, and he's going to make this a fun experience. I don't think you will find it very over the top. It'll be really a great level. And he's a graduate student. He's totally into astrophysics, and actually his work is related to large stars exploding. So in particular, he can tell us a little bit about what happened to Betelgeuse and why it's not exploding right now. Okay, so thank you guys very much. I'm going to go ahead and close shop up. Any questions right before I stop? Any questions? Any questions? Nobody watched the YouTube stream. That's fine. Great. Everybody.
Thank you.
Thank you, guys. Thank you so much. And I guess hand in your problems. Send me, or you upload a picture, right? Upload a picture or upload a spreadsheet, one or the other.
Yep, got it done.
Okay.